Red card. Obviously it was a red card.
Does Trump have to call?
I just saw more to left, actually.
Okay, I guess we can get started. So we are happy. Let's just have a few reminders of the rules of engagement. No question in the first 5 minutes. Seminar style questions, and we have 50 minutes for each presentation. And now we have Javier Bianchi talking about how small is small.
Thanks to the organizers for including the paper in the program. It's great to be here. And this is joint work with Greg Kaplan. Heterogeneous agent models have become a workhorse framework for macroeconomic and policy analysis. These are valuable models because they capture salient features of household spending behavior, and they can match quantitatively the level and the distribution of marginal propensities to consume in the data. The dispersion in MPCs is important because it matters for deviations from Ricardian equivalence. And in turn, deviations from Ricardian equivalence are really at the heart of the transmission of certain shocks, such as fiscal transfers. Following the work of Auclair, Bardozzi, Rongley, and Straub on sequence-based Jacobians, in recent years there's been an explosion of studies studying fiscal and monetary policy in heterogeneous agent models using first-order local methods. These methods are extremely useful, and it is well understood that for these methods to be accurate, the shocks have to be sufficiently small. The question we want to ask in this paper is, how small is small? Meaning, when we write and we compute our heterogeneous agents models, how small shocks have to be for these first-order local methods to be quantitatively reliable? Our answer is that for fiscal transfers, small must be very small. In plausibly calibrated heterogeneous agents models, MPCs are highly nonlinear in wealth, and in particular, they fall sharply away from borrowing constraints. Because transfers shift households out of high MPC regions, this is going to imply that aggregate consumption is going to be concave in the size of the transfers. And we're going to show that linear methods substantially overstate the response of transfers, even for small shocks. As Adrian and team have shown, when you think about, for example, monetary policy shocks, linear methods can do a very good job at capturing the full nonlinear dynamics. But monetary policy shocks are one of those cases where the heterogeneous agent model gives you very similar responses to the representative agent model. So the broader point we make is that these linear methods are going to be unreliable precisely when it is deviations from Ricardian equivalence that really drive the transmission of aggregate shocks. We also explore higher-order local methods, and we find that they can improve for narrow shocks, but then they deteriorate quite quickly. Okay, so the plan is to present what is a standard model used in the literature, stay as close as possible to those calibrations also considered in the literature, and then study linear and nonlinear responses to fiscal transfers. First, I will consider a partial equilibrium setting, and then I will do the fiscal stimulus in general equilibrium. There's going to be a continuum of households with idiosyncratic income shocks. This is a standard problem from the literature where households are going to be saving in a non-state contingent bond, and they're going to be subject to this borrowing constraint on these assets. There's a standard intertemporal Euler equation for this problem that is going to hold with equality whenever that borrowing constraint is not binding, and we hold with strictly inequality when it binds.
Here's one question. Is it somewhat important that the borrowing constraint is 0?
No, not at all.
Scaled by equal.
Well,
one of the reasons why you get this nonlinearity is because you have like share of people that move from being unconstrained to being constrained, right? If the borrowing constraint changes with the shock, then there's a smaller share of people that switches.
yeah, you could consider situations where the borrowing constraint becomes tighter with the shock or looser.
Right.
Okay, here's a benchmark which is standard in the literature, and this is what we've done so far. Okay. Once you do optimization and you aggregate, you get the aggregate consumption function, which basically tells us what is the aggregate consumption as a function of the sequence of transfers. We're going to do a very simple physical transfer policy. We're going to start at steady state and then consider a one-time unanticipated lump sum transfer at time 0. So delta is going to be the size of the transfer, and as I said, this is going to be only operative at t equals 0. The object of interest is the aggregate consumption response, meaning the deviation from consumption with the transfers minus consumption without them. So for the computation, we're going to be comparing the nonlinear solution versus the linear solution. Essentially, when we do the steady state, we use endogenous grid point, and we get basically the decision rules, and we aggregate those decision rules to get the steady state. For the nonlinear solution, we're going to use the household policy that we solved from the steady state, and we're going to solve exactly for the consumption response. And I say exactly because the shock is only at period 0, and so this consumption policy is really time invariant. So given the consumption policy at steady state, I can exactly trace what the consumption is. So we do this for every single household, and then we basically aggregate using the distribution. And still here I'm denoting the cash on hand before the transfer. For the linear solution, we're going to do a first-order Taylor expansion of aggregate consumption around the steady state. And we're going to compute the slope using finite differences, or you could use also the sequence-based Jacobian toolbox. In partial equilibrium, they're exactly identical. And so once we get the slope, we basically extrapolate and basically scale the response arbitrarily in delta. Okay, for the calibration, a period is going to be a quarter, utility is going to be log. We're going to take the earning process from Kaplan and Violante, which is basically calibrated to match second moments from annual earnings. Then we're going to take a few parameters directly from the data, and then we're going to consider heterogeneous discount factors, which there's not going to be uncertainty for the discount factor. It's going to be at period 0 fixed forever. And we're going to calibrate basically the mean of the discount factor and the standard deviation to match the mean wealth over GDP and an average quarterly MPC of 0.25. Okay, so on the right here, you see the MPC distribution. And on the left, you see the wealth distribution. As in the data, you see a large number of households with very low wealth. And here, notice that I'm chopping the distribution at 50K because there's a significantly large fraction of households with high assets, but just to zoom in the load distribution, I'm chopping it there.
What is the share of constrained agents? I can't see.
Well, as you see here, that's, it's going to be, no, there you don't see it. You don't see it there. It's going to be about 15%.
Yeah, it's 15%. That is the right-hand side.
Oh, yeah, exactly. Yeah.
It's the lowest.
It's the right axis. So you see the right axis? It's right there. Can you see it, Gianluca?
Yeah, I can see it. Yeah.
And the thing is, yeah. Okay.
Yeah. Okay.
So this is the average MPC. It falls quite sharply, close to 0. And here I'm showing you the average income MPC. Now that's going to be fairly, I would say, very slow slope. And then this is the low income MPC, meaning I take a household with very low income, and I trace the average MPC, and that's basically, you see this cliff in the sense that the MPC is going to be 1 at the borrowing constraint, and then as I move those assets away from the borrowing constraint, there's going to be a discontinuous drop in the MPC. That's going to be playing an important role. Okay, so this is the aggregate consumption response as a function of the size of the transfers. Okay, that's the red line. So here is the nonlinear consumption response. You can see it's concave. And you can see that the linear method overstates quite substantially the response.
What's the time period here? So this is just on impact?
This is on impact, yes. In the paper, we also look at the whole transition sequence, and I'll show you maybe later some of those simulations. So on impact, at a 5% of GDP, which is about $8,000, the linear method overstates the response by 42%. At 0.5%, it still overstates it by 17%. Okay, let me try to go deeper into the reasons why this consumption function is concave. And what we're going to argue is that there are two motives for this concavity. One is the familiar one that comes from the curvature of individual consumption from Carol Kimball and others. The other one that we're going to highlight is this feature that households are going to move on and off the borrowing constraint in response to the transfers. This is the aggregate consumption in period 0 as a function of the transfer, where remember that X tilde is the cash on hand before transfers. So, and G here is the initial distribution over cash on hand before transfers. And I'm going to denote by X bar of Y the level of cash on hand at which the borrowing constraint stops binding. Okay, so a household is going to be constrained whenever its cash on hand before transfers is less or equal than X bar of Y minus delta. So with this, I can now split the consumption between those that are constrained and those that are unconstrained, okay, where the limits here of the integral precisely capture how the transfers are shifting households of the borrowing constraint. The MPC, as I mentioned, has a discontinuity at the kink, okay, at the point where the borrowing constraint stops binding. And using this result, basically, I can now differentiate that aggregate consumption, and I basically get a weighted average of the MPCs. Okay? So this is going to be the average MPC for those unconstrained households and this is the MPC of the constrained households, which is equal to 1. And lambda bar here is going to denote the share of households that are constrained at steady state. Okay, so what does the linear solution does? Well, it takes basically this, this steady state aggregate MPC, and then it extrapolates. What this means basically is that changes in the share of constrained households are going to be irrelevant to a first order. It is as if households that are constrained remain with an MPC of equal to 1 no matter how large is the transfer. Okay, so this is again the first order derivative of the aggregate consumption function. Now we can do the second order derivative, and you get basically these two terms. This second term is a familiar one, which is the consumption curvature of individual households. And this basically is just summing across the second derivative of those individual consumptions. The first term here is capturing basically this movement on and off the constraint. The term here in brackets is the drop in the MPC, how the MPC goes from 1 to something below 1, strictly below 1, once an agent becomes unconstrained. And this lambda prime is the change in the constraint share. Okay? Once you give the transfer, there are going to be some households that are going to switch from being constrained to being unconstrained. And that change is this lambda prime of 0. So now we have these two terms. This is negative. This comes from Carol Kimball. And this is also negative because as you give more transfers, this constraint share is going to fall, and this term is going to be positive. Okay, so this explains the concavity from the aggregate consumption response. Now, we do a simple decomposition of this gap between the linear and the nonlinear solution. So the blue line is the one I showed you before. That's the nonlinear. The red line is the linear I showed you also before. And this line here, basically what I'm doing is I'm keeping the share of constrained households fixed at the steady state value, and then solving fully nonlinear the unconstrained households. Okay? You can see that gets me closer to the nonlinear, but it's still quite far. So just in terms of numbers, this suggests that basically a large share of this concavity is coming from this movement on and off the constraint.
So you took a log utility function, so you were quite conservative with the curvature of, what about sigma equal 2, for instance?
Yeah, we did it at some point, but on top of my head, I cannot tell you the decomposition for sure. This will change, yes.
The surface of the area of the red.
Yeah, we should have that. I agree. There are other ways of doing this decomposition, let me say. So another way we do it is we say, okay, let's take the exact share of constrained households, which we know from the nonlinear solution, and then we take the unconstrained households, we just take a first order Taylor expansion. And when you do that, you get actually very similar numbers to those here. Okay, so it's really driven by this change in the share of constrained households. And here is a picture that shows that. Okay, so this is the change in the share of constrained households as a function of the transfer. Okay, you can see it falls very sharply. Okay, and then at some point it has to flatten out because all households eventually will be unconstrained. But it falls quite sharply. Okay, for small levels of transfers. So taking stock, what's shown you so far is why these linear methods overstate the response to transfers. Well, in the linear solution, these changes in the constrained share of households have zero first-order effects. And in the nonlinear solution, there's going to be a substantial change in the share of constrained households, which have a very different MPC. And so that gives you a fairly substantial gap between the linear and the nonlinear solution.
So yeah, I guess how quickly it goes down depends on how constrained the constrained people are. So do you have a sense of what in the model, what parameters in the model sort of discipline that thing, and whether we kind of can get a sense of in practice?
Yeah, we're not targeting that number. We're targeting the level of wealth. We're targeting the average MPC, and this is a moment that comes from the simulations. I can see if you have higher risk aversion, for example, then probably less people would pile up against the constraint. But then, it's still all about this, right? It's not so much about the level of households that are at the constraint at the steady state. It's about the change.
Yeah, no, but that's what I have in mind. It's about how big is the Lagrange multiplier. So do we know how to discipline that in the
Yeah, how sensitive is the Lagrange
exactly.
multiplier to the transfer? Absolutely, absolutely, and that's a good point, I think, to explore more. Okay, so I want to, yeah.
And I have a related question. So, why do you, in the previous slide, how do you explain the kink and the lambda prime is 0? Because Lagrange multiplier should be more or less continuous in the transfer size. So we would expect this function to be continuous in the transfer size.
No, it is continuous. It does have some.
I would say,
It is
more regular, not the kink.
with discrete income shocks, which is what I'm showing you here. It has some, some non-differentiabilities. But I'm going to show you later that once I do it with a continuous distribution, you get essentially the same numbers. But it's all about how, you have people at the constraint, but are they close or are they far away? So if they are close, a small transfer is going to push all those agents to be unconstrained. So that's why you see this sharp drop. And then here it's telling you there are some agents that are very impatient. So for those agents, no matter how big is the transfer, it takes a huge transfer for them to become unconstrained. Okay, so I have here several robustness exercises, just because I want to make it clear that the results are not driven by a specific calibration, even though we try to stay as close as possible to the literature. So on the x-axis, I have the size of the transfer. And on the y-axis, I have the linear to the nonlinear consumption response. So a value of 1 would mean basically that the two solutions are aligned. A value above 1 means the linear solution is overstating the response. So that's the baseline.
If you think about, you're showing us this region, but the empirically relevant region is from 0 to 0.5%, right?
Really? 0 to 0.5%. Like in COVID, the checks were 12%.
But no one's using linear methods for COVID. I mean, that's insane.
Well, there are people using. We can, this is you have all the range. If you're interested in shocks that are 0.1%, you can, this would tell you you're fine with. You're relatively fine with linear methods.
Also, there's $2,000 per person, right?
Yeah, I'm happy to discuss more. What is the more plausible levels of transfers. I think that's more of an empirical question. Here I'm giving you the whole menu, and then you gotta make the choice whether you're gonna use linear methods or you're gonna do nonlinear.
So one comment here also on next to what the object is, and this goes back to my previous point on the y-axis. So here this is showing us the ratio for an impact. If I instead do it over lifetime, this is always going to be 1 because everyone will eat everything,
100%.
right? So then I guess it would be useful to show here what happens as I increase the horizon, like say do it over a year, because that's what
100%.
we usually care about, right? Cumulative multipliers.
We have that in the paper, and I think in some backup slides I have it as well. I will be able to show it. So this is the baseline. This is a case without heterogeneity in discount factors, keeping the same target for assets. This is again without heterogeneity in beta, and now calibrating a higher asset to GDP ratio. This is a case with stochastic beta. Okay, there are some changes, but nothing very substantial. This is a case with finite lives. Again, not much changes. With lower transfers, you get a little bit less nonlinearity because now households are going to be saving more out of the borrowing constraint. This is the case with natural debt limit. Okay, not surprisingly, also you get much smaller nonlinearities because now there's actually no binding borrowing constraint. Yes, households are just subject to a natural debt limit. Adrian?
Can you talk more about the lower transfer case? Do you mean in the steady state?
Yeah, in the steady state.
Transfer is less?
Yeah, in the steady state.
But your steady state transfer was like 15?
We calibrated the level of transfers to what we see in the data, and this is basically lower transfers. Maybe it's 30% less. I forgot about exactly numbers. It's just scaling down those steady state transfers. This is one case with labor supply, endogenous labor supply, which we're going to have in the full Hank model. And finally, here, instead of taking that stochastic process from Kaplan and Violante, we use the one from Auclair, Rongley, and Straub. And here you get like significantly larger nonlinearities.
Why is that?
It's much larger. It's a much larger variance of the shocks. Huh?
It's a much larger.
Much larger idiosyncratic income risk.
So there's more curvature in the consumption.
Yeah, there's now going to be more concavity coming from the pure Carroll-Kimball. And then the Lagrange multiplier on the borrowing constraint is also going to be higher because now you're still getting hit by these bigger shocks. Okay, and this basically we took it straight from that paper. Okay, so you may wonder, well, okay, you have this our focus was really thinking about these nonlinearities, how big they are, but you may wonder whether if we do higher local approximations, we can get close to the fully nonlinear solution. And what we find is that a second order approximation in fact improves, as you can see here in this left plot, but it does so only for a fairly narrow range of shocks. And then you can see here it deteriorates very quickly. So what's going on? Well, that goes back to the second order Taylor expansion that I showed you for aggregate consumption. There's a term here, again, that is this change in the share of constrained households, which is basically the density of households at the kink. Marcus?
I wanted to ask you, so you have this half constraint, this half borrowing constraint, if you had a smoother one, would it be equally chromatic or would it be less chromatic? And how smooth do you have to smooth it out?
So we haven't done it. My hunches would be everything else constant. It's likely to be less dramatic, but that's keeping everything else constant. I have to think more through the whole equilibrium to how and compute it too.
Can I just follow up a little bit? I mean, this is a bit orthogonal a bit to this, but I mean, so this type of like fiscal stimulus experiments in practice they occur in recessions. And recessions are times where we think borrowing constraints tighten asset values that fall or income. And in that case, the share of people who, thanks to the transfer, will switch status would be much smaller.
Would be much lower. Okay, I thought you were going to say the opposite. I thought you were going to say, now instead of starting from a 15% share of constrained household, they have from 25%. So as I start giving transfers, now the potential amount of people that would switch from being constrained to unconstrained would be larger.
Well, not to the transfer. I mean, the transfer itself will not lead to people switching status with a shock.
Okay, so I think let's make sure.
So
I'm completely with you that.
Maybe this has the same implication for the linearity versus nonlinearity, but it wouldn't be the transfer itself.
Okay, so here's what I would like to do. We haven't done it, but instead of starting at steady state, let's start from a low income state, aggregate income state, and then let's see what the transition would look like without transfers, and then do the same transition with the transfer. My hunch would be that to the extent that we start from more agents being constrained, there's more potential for transfers to create this nonlinearity. That's my hunch.
But, I mean, as far as I understand, you need the share of people switching status to be large.
Yes.
So if they remain constrained.
No, 100%. If they were to remain constrained, but you're saying, oh, the Lagrange multiplier is so high that it really, everybody's very far. That's
because the constraint factor.
That's possible. It's going to depend, as we were discussing with Luigi, where is the distribution? Is it close or is it far away? I agree with you. It will be interesting to do. So why is the second order doing so, poorly for medium-sized shocks? I would say. So when you do this second order Taylor expansion, basically we're extrapolating here the change in the constraint share using the density at the kink. But of course, once you increase the transfer, that change in the share is going to start falling at some point. It will flatten. And that's why the second order gives you basically an understatement of the response to physical transfers for, modestly large shocks. And if you do a third order, this problem gets compounded because now there's going to be the curvature of the share of constrained households that it's going to show up. And the third order approximation is going to overshoot even further. If you start very close, you do better. You cannot see it here, but you do better with the third order. But very quickly, the third order gives you a worse approximation, even than the linear or on the second order. And again, this is not a specific calibration. Here I'm showing the same plot I showed before for the second order to the nonlinear consumption response and the third order to the nonlinear response. So you can see here that you can very easily get worse approximation compared to the linear one. And I want to go back to this plot, which is the change in the share of constrained households. Now, talking to a few people, some concerns were raised had to do with the fact that here we're considering discrete shocks. So if you do a continuous shock, so you do now quadrature and you consider a continuous income shock, keeping basically the same calibration, this gets a lot smoother, right? The red line now is going to be very smooth with respect to the transfer, but overall it has the same shape. And from here you can also infer that it's still going to be hard for local methods to be accurate because this eventually is going to flatten. The red line will flatten. So how are you going to capture that with a polynomial? I mean, I'm not saying they can never work. I'm saying we did something that is fairly standard. It doesn't work. Maybe somebody, maybe next paper we'll see. Maybe there are ways to do it better, and I'll be super happy to see that. And this basically shows you the ratio again of the second order to the nonlinear. Now comparing the discrete distribution, which is our baseline, with the continuous distribution. Okay, so yeah, naturally the one with the continuous income process is smoother, and it does better, but then still very quickly it ends up understating the response to the transfers. Okay, now I'm gonna do the fiscal stimulus in general equilibrium. So I'm gonna take that partial equilibrium problem that I showed you. I'm going to add production, labor supply, nominal rigidities, and fiscal and monetary policies. Households now are going to have utility over consumption, and this utility from labor, and their income is going to be their labor income plus their dividends. We're going to have, as in Adrian's team, we're going to have this labor union with sticky wages, and we're going to take directly the linearized Phillips curve because we really want to focus the analysis of nonlinearity coming from the borrowing constraints and the incomplete markets. There's going to be a linear production function, flexible prices, that's going to be our baseline. And so we're going to have wages equal prices and dividends equal 0 in equilibrium. Okay, this is the government budget constraint. There's a fiscal rule for the government. So whenever this debt is away from the steady state, the level of transfers is going to be adjusted so that debt reverts back to the steady state. And then for our baseline, we also do a standard Taylor rule. Okay, for the Hank model, there are going to be several other parameters to calibrate, which are fairly standard. I'm not going to go through them. And for the computation, we're going to take directly the sequence-based Jacobian toolkit, and then we're going to solve the model, the transition, non-linearly through a quasi-Newton algorithm. And let me say, we don't innovate at all in the solution method. At the end of the day, we have just a vector with market clearing conditions, Phillips curves, and we're just finding the sequence of output, inflation, that is going to give me a 0 of that vector. And it takes a few more seconds than the linear solution, but it's
Why not use the sequence-based Jacobian for that one?
So
the SSJ toolkit has a quasi-Newton algorithm in it.
We could have, we could do that as well. Okay, so before I show you the simulations from Hank, I want to show you first the flexible price allocation. Okay, in the flexible price allocation with these unions with these labor unions, you're not going to get any output effects. Okay? So all the effects of fiscal transfers on the aggregate demand for consumption is going to translate into the risk-free rate. And what you see here is in the linear solution, you get fairly substantial real rate responses. Okay? So essentially, the linear solution is overstating the response of fiscal transfers, and it's giving you I would say, an implausibly high R star. Okay, so for the Hank, this is the picture. So same, we have transfer size on the x-axis, and we have the linear response for output and the nonlinear response. At 2% of GDP, the linear solution overstates the response by 34%, At 5%, the linear solution overstates it by 50%. And I have here the 4Q response that I'm tempted to go through. And that's it here, okay? So this is the nonlinearity from the 4th quarter. As you said, once you do it for sufficiently long period of time, it's going to be 1. So
here, not necessarily. In the PE, necessarily.
in the PE, that's right. Okay, so again, robustness in Hank. So this is the baseline. Then we're going to be looking at different cases. This is the constant real rate rule. This is a faster fiscal adjustment. Okay, so households now that are initially constrained, when they know they will be taxed in the near term, they are more willing now to save, so they will become unconstrained. That's why you see more nonlinearities. This is nominal bonds. Doesn't make a difference because inflation is just too small on impact. We do a case with sticky prices too, and with the union labor, and it's quite close to the baseline. We also do sticky prices where households are choosing directly the labor. And again, that's very similar. We do an FTPL case. And there, the nonlinearity becomes significantly less important, but that's because the way the FTPL works is that now you're getting an expansion in output that is completely orthogonal to the borrowing constraint and the market incompleteness. Okay? So that response is more linear. Good. So we have a few more results in the paper. So let me show you a couple of these. So just like the concavity of the consumption function means you overstate for expansionary fiscal policy, now you're going to understate in response to a contraction in transfers. Yeah, and you get slightly larger nonlinearity for contractions, actually. So the linear method also understates the persistence. Okay, and this is related to Christian's point. So whenever you do it nonlinear, now you have households that are saving. So starting from the next period, that means that their demand is going to be higher, and that overall, that means you get a higher output, okay, under the nonlinear solution as of period 1. Okay, so the linear method gives you an overstating on impact, and then it understates the persistence of the shock. And naturally, in general equilibrium, this translates also into different persistence for the real rates and for inflation. Okay, so our baseline was one where we're giving every single household the same amount of lump sum transfers. In practice, it's more likely that we would see transfers targeted towards the bottom of the income distribution. So if we target basically the 20%, the bottom 20%, that's the picture, okay? So here's the comparison. So this is our baseline. The transfer is to all households identical. As you start targeting more and more the poor households, this is the bottom 50, you get a larger gap between the nonlinear and the linear solution. And we do the bottom 20%, which is the equivalent to this plot here. You get substantial.
So Javier, here is the same amount of money. So basically, the transfers are becoming bigger and bigger, and it's more likely to move people outside the constraint.
100%. So I'm keeping here fixed the total amount of money the government gives. I'm just giving it to fewer people. And here, Kurt, you'll see that even if you give it just to the, you take maybe 1%, you would get, in a realistic case, you would get a fairly substantial nonlinearity.
But I think, like, if you want to think about COVID, the rate target transfer, the people, their income went to zero. And then
I'm
their
saying,
income
it's
back
saying
to
if you
one,
think 10% is
so
too
it's
big,
zero.
if you think 10% is too big and you give just 1%, you'll get a big gap.
I'm saying, for lump sum transfers, it's like $500, $1,000. If you want to think about UI, that's not what your experiment is about at all. It's people whose income went to zero and then their income was replaced. And my guess is that there might be something down the areas, but you should do that if that's, if you want to kind of look at the big transfers during COVID, that's what it was.
Good. So this is the case where I do here monetary policy shocks and TFP shocks, and this is something that Adrian and team have already shown that when you do monetary policy shocks, you get something that where the linear solution does very well. Okay, and the same is true for TFP shocks.
For monetary policy, or is it not exact?
No, it's not exact. No, it's not exact.
So why not?
Why
You
would
have
it?
a calibration where it's not?
I don't think in your paper it's also exact. It's very close,
No, it is.
but it's not exact. It's not exact.
No, it's true nonlinearly. Under the right conditions.
Well, I don't know what you mean by right conditions. Under these conditions that I'm considering here, they are very close. They're not exact. I'm sure you can, cook situations where the two are the same, and those are going to be cases probably where the hank is also lined up with the rank. Okay. So that's the conclusion. Okay. First order methods significantly overstate the effects of fiscal transfers. And what is really key is that higher transfers shifts households out of the borrowing constraint. And by doing so, this is going to lower basically the aggregate MPC. There are cases where, again, these linear methods work very accurately, but those are cases where there's very little difference between the hank and the rank. So the broader point is that if you want to think about transmission of shocks, where these departures from Ricardian equivalents and incomplete markets are driving the response to macroeconomic shocks, it's important to consider nonlinear solutions. Thank you.
We still have 3 minutes for questions, so let's open it. I do have a question. So, have you thought about shocks that directly affect the borrowing constraints? Like, suppose I do Guerrieri and Lorenzoni and I do the linear, and now I do something nonlinear. Would you expect to get kind of because of the fact that now the fraction of people that are at the constraint is going to change?
100%. I think those would also be very likely to give you very high nonlinearities. For the reasons you.
To add to the paper, I think.
I agree. Thanks. No, thanks. It's good. Can do that.
Small point, but I would think probably the middle point would have to be revised somewhat in the sense that, a monetary policy action will necessarily require some kind of fiscal reaction in the background, depending on what exactly the fiscal backing is. The conclusions from the first part will be imported to any kind of monetary policy experiment, right? Whether you have fast or slow adjustment underlying this, it's going to be as if you have like a baseline monetary action plus an additional fiscal transfer, tax, whatever action. And to the extent that the effects you characterized are there for stimulus checks, they will be there, given because a monetary policy action is just going to put a hole in the government budget if it's a rate hike, and that'll necessitate an adjustment. So I think, like in general, just in these kinds of environments, all shocks will in some sense be shaped by the departure from recurring equivalence.
That's a very good point. And
It's actually related to the question I had, because if you have no government debt at all, then there's no fiscal monetary interaction.
Yes.
Then you get exact nonlinear.
Yeah.
And so it's the same.
Yeah.
It's actually the same thing.
so here you have some fiscal and monetary interactions. You have them, but you could have different assumptions under which those interactions become stronger.
Yep.
And then, I would suspect that, to the extent that this ends up affecting the share of borrowing-constrained households, this may also lead to important nonlinearities, even in response to monetary policy shocks.
Great. Thank you.
Thank you.
So the next speaker is Matt Romsby, and he's going to talk about higher order perturbation in the sequence space.
All right, thanks so much, everyone. Thanks, Javier. So this paper is about higher order perturbation in the sequence space and something we call the certainty correspondence. And it's joined with Adrian and Ludwig, who are right there, and Rodolfo, who's not, but if you don't know him, he's absolutely terrific. So here I'm going to be presenting our paper through most of the talk, but don't worry, I will, address some of the questions that were talked about in the last presentation through the course of mine. But first I'd like to start from something that we all know in the HA world, which is that heterogeneous agent models with aggregate risk are difficult to solve. And so a very common strategy, one that Kurt and team helped introduce, is to solve with perfect foresight for small shocks and then appeal to what's called certainty equivalence. And certainty equivalence says that first order perfect foresight is actually equivalent to the MA process in a full first order perturbation solution of the model. Now, this is a very, very powerful tool, and Javier has some critiques of it that I'll get to, but there's a general critique that this kind of thing is not suitable for questions in which aggregate risk and nonlinearities and all these interesting things play a key role. This is part of Ben Moll's critique. What we're going to show is that actually to higher order, when you are dealing with those nonlinearities and aggregate risk, there's something we call the certainty correspondence. And the certainty correspondence says that actually from perfect foresight, MIT shocks alone, you get enough information that you're able to solve for the second and third order perturbation solutions of the entire heterogeneous agent model with respect to aggregates. This applies to non-HA models too, but of course it's most useful for HA models. We're going to spend most of the talk talking about sort of fairly straightforward income shocks, but we're going to build up at the end to two big quantitative applications with time-varying fiscal multipliers. Oops, right here. Time-varying fiscal multipliers and nonlinear Phillips curves. And one thing I want to emphasize is that we're going to get the exact same solution as the so-called prune state space solution. I don't know if Jesus is there, but Jesus and others have worked on their contributions to that. We can validate that we get exactly the same in cases where we can solve both models using either thing. And that also, in cases where we can get a full global solution, in practical cases, we often get quite close to the full global solution as well. This solution is much more practical and much easier for HA models than either of those approaches. Okay, so let me talk a bit more about the certainty correspondence before we get started. So over on the left, I have the perfect foresight solution, where agents don't perceive aggregate risk, but they might be hit with shocks kind of unexpectedly. And on the right, I have the rational expectation solution, where agents have correct expectations of aggregate risk. And then we can perturb both of these in kind of the order of aggregate risk that we face. So to zeroth order, we have the deterministic steady state on both sides. To first order, we have this Bopart-Crissell-Mittman first order certainty equivalence response, or a result, which says that the first order perfect foresight response, which you can get from a small MIT shock, gives you a linear MA representation of the full stochastic rational expectations economy. So what we're going to show to higher order is that if you look at second or third order perfect foresight responses, so literally second and third derivatives of like MIT shock responses, you can get the components that let you build a quadratic or a cubic MA process that then you can use to simulate the economy. These quadratic and cubic MA processes are sometimes called Volterra expansions. Some parts of them are easy to get. The parts with respect to kind of realized shocks are easy to get. The parts with respect to risk are harder to get, and we'll show you how to get both of those. All right, so let's get into our setup. Yep?
Just to make sure, so the second order product is not time-varying aggregate risk, just derivative.
No, this is a perturbation with respect to one parameter, which I'll show you in a second, that's kind of indexing the overall level of aggregate risk. I think with our third order solution, you could get some things that are kind of endogenously similar to time varying aggregate risk. That's not a case we focus on ourselves. So for our setup, we're going to try to write kind of the most generic overall framing of a macro model, where we're going to assume that there's some n-dimensional F equation that takes in a vector, also n-dimensional, where n can be really big for a head agent model. It takes in lagged x, current x, and expectations of future x, plus a shock with mean 0, this epsilon. And basically what happens is that the x at time t is pinned down by the state, xt minus 1, the shock, epsilon t, and then rational expectations. So we're going to assume that these epsilon t are distributed with volatility sigma r in reality, but that agents take expectations assuming that the distribution is scaled by sigma. And in the rational expectations case, which is what we're ultimately after, sigma and sigma r will be identical. But we also want to consider this perfect foresight case because that's the way that we define MIT shocks in the first place. So in the perfect foresight case, sigma equals 0, so the expected epsilons are all 0. People think no shocks are ever going to happen. But then sigma r is positive. Some shocks actually do happen in practice. Okay? So this is our framework. Some people have written very similar expressions, but sometimes they put the expectation on the outside of the F. We show that we're able to put all the models we want in this framework. You could also write them this way, but this turns out to be very nice as a convention for getting the results we'll show you a bit later. So this is the general setup. And in the paper, we show several models that can work within this setup. I should add, by the way, that the deterministic steady state X is just what you get when there's no shocks. But the example that we're going to work through for almost all of this talk, at least on the partial equilibrium household side, is a standard incomplete markets model, which I'll define here. But it's basically the same model that Javier showed you. Even the calibration, I think, is fairly similar. Where agents choose between allocating their resources to consumption or assets next period. They carry in some assets from the previous period, and then they have idiosyncratic income risk with a borrowing constraint. So our key point here is that the persistent risk is going to follow a discrete Markov chain, like people normally calibrate, but that we're also going to have this xi right here, which is an additional IID shock, mean 1, with a smooth density. And as I'll show you in a minute, that's really going to help to smooth things out and make the model much better behaved mathematically. Aggregate income, Z, which just scales kind of this labor income process right here, we're going to assume it follows an AR1 process, but we could easily assume any other process. We're going to consider a bunch of just one-time shocks for most of the paper. And then down here, I'm just going to put kind of the bookkeeping of how you would define all the parts of solving this thing to put it into that F function language that I showed you on the previous slide. And I'm not going to dwell on how that works, but there's things like, there's iteration over a value function, those equations are in the F, iteration over the distribution, those equations are in the F, right? And it's important to note that, expectations, that forward-looking part, in this model, that's going to enter through expectations of the value function, right? So this is going to be the kind of standard model that we're going to use, and it can be put into our F function language. Okay, so I'm going to take a brief detour, just because I think it's really important, especially in light of the last talk, to talk about why these xi shocks, these IID smooth income shocks, why they're so important. And the starting point, which I think a lot of people who have worked with these models know, is that when you simulate them with discrete income shocks, they tend to have lots of kinks everywhere in the policy function. And then they also have lots of mass points everywhere in the distribution, right? In fact, you can prove that if there's discrete income shock processes in this model, the entire distribution is mass points. That's a mathematical fact. But if we have a smoothly distributed component of income, and when we implement it on the computer, we are very careful about making sure we preserve that smoothness. We don't just discretize that smoothness into a few points. Then we get a much better behaved function. So over here, I'm just plotting for our calibration, which you can see in the paper, but pretty similar to Javier's. The consumption function is a function of cash on hand. This is all for the lower patience state, by the way. The higher patience guys are more boring. You see, people, there's one kink where the constraint stops being binding, and people stop spending all their cash on hand and they start spending a little bit less, but there's no other kinks. Everything's beautiful and smooth afterward. And then over here, where I plot the CDFs of assets, there's a mass point at 0 at the borrowing constraint, but there's no other mass points. Everything else is sort of beautiful and smooth. And if you've worked with these models in practice, you know that without carefully smoothing things, you don't get that, right?
So,
Yeah.
so how big do these sign need to be? Because you are also, I understand you're smoothing, but you're also introducing IID-ness in the...
Right, so we actually calibrate based on some recent evidence. We have sort of a serious calibration strategy based on evidence in a paper by, Pascal Noel and co-authors of, of quarter-to-quarter volatility in income. So we use that to calibrate. I think it ends up being like on the order of 0.10 or a little less than 0.10, 0.07 or something. You don't need it to be that big.
0.10% of the variance of income? Or?
0.10% of the cross-sectional standard deviation, so 0.10 in logs. There's a surprising amount of quarter-to-quarter income variation in the data. I don't think for the technical aspect we need it to be like that, but we just decided to try to take something from the data to calibrate it.
So what's the advantage of doing that over just doing a continuous state distribution?
Great. So I think if you just did a continuous income process and you were very careful with it, I think it would be fine. The problem is it's kind of really hard to get that right because you have to, ultimately on the computer, you have to somehow discretize the continuous income distribution, right? And then you might need a lot of points and to be very careful to get it right. So we represent all the persistence with kind of a usual discrete Markov chain. And then when we add the IID part, that doesn't add any states to the model, right? Because it's just an IID thing, so it just changes cash on hand today, but it doesn't change any of the, it doesn't introduce a persistent state.
Economizing state.
So it's essentially economizing on states, just making it a little bit less of a departure from the standard way of doing things. So this is smooth, which is not what you normally get. And what are some consequences of that? Well, this becomes really important as we start taking higher order derivatives, right? Because, kinks corresponds to points at which the second derivative of the consumption function is infinite, right? And so, if you have people, mass points that might be at kinks or might not be at kinks, you can get really irregular results when you try to differentiate the model. If you smooth it out like this, then you get very regular results, as I'll show you right here. So what I'm going to do is I'm going to differentiate the model numerically, and basically I'm just going to do a simple shock, a one-time income shock that scales everybody's income at date 0. And I'm going to look at the date 0 consumption response to that. I'm numerically differentiating as I vary the step size h with which I'm numerically differentiating. And Javier and Greg have a few plots in their paper where they try to do this and they show, oh, it doesn't work, it's going crazy, right?
Wait, I just told you today that we were concerned about the discreteness of the shock.
Yeah, you introduced, but that's not in...
We put more discrete states.
Yeah.
At that point, we get exactly the same. And today I show you results where we use quadrature, where the income shock is continuous.
Yeah.
And yeah, you get something smoother, but still the approximation becomes 5 once you go shock.
Sorry, but the thing about continuous, that's the first time I've seen it. It's not in your paper.
No, it's in the slides.
It's in the slides, yeah. But I think most of the results are still from the non-continuous thing, right?
I show you today that the results are, I show you on top of each other, the baseline with the discrete shocks, and on top of that I show you the ratio of the second order to the linear with the continuous distribution. It gets slightly better, but it doesn't make a big difference.
I think it was a fair amount better, and what I want to add here is that it depends a lot on how you do the implementation. You have to be very careful about the implementation. This is where like all the kind of perfectionist things where I kind of get my, I see some of my students in the room, where I berate students, in second year about it, they come into play. So when you do quadrature, for instance, you need to do quadrature separately on both sides of a kink, right? Rather than doing it, naively across the kink where quadrature rules don't work that well. And you need to have cubic splines instead of linear interpolation, et cetera, et cetera, et cetera. So what I do here is I have our smooth model that kind of does all those things properly versus a non-smooth model, which I'm just doing the exact same calibration. I have, discretization of the same IID shock with 5 points, and then I apply more standard methods with the non-smooth model, you can see the smooth model has incredibly regular numerical derivatives, right? Everywhere, the numerical derivatives are sort of standard. And whereas the non-smooth model, the numerical derivatives are going crazy, depending on the h, right? So what I want to impress upon you from this is that numerical differentiation can work very well. It's very stable if you have a properly done smooth model. If you don't have a properly done smooth model, then you can get very misleading results. And for second order, at least it's not like orders of magnitude off, but it's very inconsistent, and it's still like a factor of 2 wrong no matter where you look, okay? And this is something we've been harping on for a while. It takes a lot of careful implementation, but smoothing works for second plus order differentiation. And so for instance, if you want to go to the GitHub for our MBR workshop last year, which coincidentally was held in the same room, I gave a lecture about this in this room, we have the smooth model from that. Okay, so now with that departure out of the way, where I'm kind of clarifying that you can use numerical differentiation, it agrees with what we've done with analytical differentiation for an HA model. Now let's go to the stochastic sequence space solution. So we're going back to kind of the generic setting of this paper. I'm going to, given sigma, given a level of risk, define this solution as a function of sigma and all the past epsilons that have been realized. And the idea is if you know all the epsilons that have been realized forever, and you know the sigma that people have been expecting both today and in the past, then you can piece together what the solution today is going to be. And this is not a new contribution entirely on our part. Lon and Meyer-Gotha actually have the exact same concept. Lombardo and Uhlig have almost the same concept, they just don't have an infinite history of shocks. But you can see the contrast with the state space solution, right? The state space solution, this G down here, it's a function of lagged X, epsilon the shock, and then sigma the risk, right? Now, the solutions we show in the paper are equivalent, so you could even get the sequence space solution by kind of iteratively plugging in the state space solution and kind of rolling with it, but we're going to do something different. We're going to relate it to the perfect foresight solution, which is almost exactly the same, but it has sigma equal to 0, okay? So you can think of the perfect foresight solution as a case where everybody assumed that there was going to be no risk forever, and then every time, they're surprised with a different epsilon that they didn't think was going to happen, right? So it's just one argument different in the function, but it's a very different kind of concept. And then we're going to use a perturbation approach. We're going to perturb this curly x around the steady state and show that we can get the derivatives of this, that we're going to relate the derivatives of these two things to each other. And one helpful result I want to mention is that the model, we assume the shocks are symmetric, so scaling by sigma or scaling by negative sigma is exactly the same thing, right? So that means all the odd derivatives of x are going to be 0, so we're going to be able to kill some terms in our perturbation. That's not strictly necessary, but it makes our life a little bit easier. Okay, so with that in mind, I wanted to define a very special case of perfect foresight called MIT shock impulse responses. So MIT shock impulse responses are where there's literally an MIT shock. An MIT shock is where no one ever expects any risk, and then one day there's a shock that no one expected, a nu, right? And then at that nu, after that, there's never any shock again. Or that's the conventional MIT shock. We define xj MIT of nu to be the impulse response to that j periods after the shock, okay? And that's just a super special case of our sequence space solution. Now, we all know different ways to compute MIT shocks, right? That's the whole Beaupart-Crissell-Mittman insight, that that's something that is more practical to compute, so then it's useful to leverage. So, this is something, we have advice on how to compute this, but this is something a lot of you can already do for a lot of the models you want. I'm also going to define a sequence of 2 MIT shocks as sort of another special case of X. What this is that, first there's an MIT shock. Everyone's surprised. They're like, oh, I didn't think a shock was coming. And then no one thinks a shock is coming again. And then another shock comes on top of it. It's a little harder to solve that, but it's still pretty easy, right? You just solve for the first MIT shock, you figure out what's going on, and then you overlay another MIT shock on top of that, right? So it's very practical to do, and you can compute this guy as well, all right? And so we're going to use both of these for our second order perturbation. So why are these sufficient to get the second order solution? That's where I'm going next. Why are these sort of simple, goofy MIT shocks enough? Well, warm up, I'm going to just do the Beaupart-Crissell-Mittman thing. So let's first expand to first order. We get this sort of first order Taylor expansion of the x. And then with that first order Taylor expansion, I'm first going to note by symmetry there's no direct derivative with respect to the sigma. That's the certainty equivalence. And then I have all these lag terms in the epsilons. And you note that they're being multiplied by derivatives that are around the deterministic steady state. So these derivatives of the x are taken around the steady state where there's no anticipated risk, there's no other realization of the shock, right? So these are just, first order derivatives of responses to MIT shocks. And so we can identify them, we can identify these terms right here as just the impulse responses to MIT shocks. The jth period of the impulse response to the MIT shock is exactly the jth, lag in the MA representation of our economy to first order. And this is not a new result. It's Kurt's result for head agent models. It's certainty equivalence saying that to first order, you get a linear MA process that you can just read off from the MIT shock first order responses. Okay? Very useful result. Now, I'm going to go to the second order certainty correspondence. So I'm just going to kind of do the same thing. So I'm going to expand a second order around the deterministic steady state. I'm going to use the symmetry result to kill the terms that have only a single sigma derivative in them. So we don't get every possible configuration of terms. And then in parentheses here, I have all the new second order terms that we're introducing. So you'll see here first we have kind of double derivatives with respect to every path shock, right? That's not that surprising that we get those terms. We get these quadratic interactions between path shocks. And then we get this x sigma sigma times sigma squared. That's a representation of the risk, right? That's the risk term in the second order solution. You'll note that it doesn't multiply any epsilons. In the second order solution, we don't yet get any interaction between the risk and the observed epsilons. So again, these are derivatives around a place where there's no anticipated risk or past realization, and we're multiplying them by these products of the epsilons. So this is what we get to second order in principle, and then the question is, where do we kind of get these derivatives from? Like, how do we actually compute these? Yep.
So is it important that you do it around the deterministic steady state, or you could take it, because typically once you start going higher order, it could be that the ergodic distribution somewhere
starts going far. So the way we're doing everything, it's always around the deterministic steady state. And that's kind of the only way we've been able to sort of successfully think about things. But I will show you a little bit later that one of the third order terms is essentially just taking derivatives around the risky steady state. So we're able to equate part of the third order solution with a strategy like that.
So there is some structure that the deterministic state gives you here.
Yes, it gives you, yes, I think because just the MIT shock thing in general is taken around the deterministic steady state. Now, again, I'll show you that you could take it around the risky steady state and that'll get you part of something. But in most cases, the deterministic steady state is sort of the easiest object. So we think it's the best starting point, maybe not the only one. So what we're going to do is kind of rearrange these new terms and interpret. So I'm just going to break them into three. It's basically the same thing you already saw, but we have, on the second order terms, we have an anticipated risk term. We have a size dependence term where you get the quadratic in a given epsilon itself. That size dependence term is saying, how does the affect the impulse response to a shock change with its size? And then there's state or history dependence, which is how does the response to a shock change via its interactions with other shocks that have already happened, all right? So we have these three things. And as you can probably already guess, the size dependence and the state dependence you can get kind of immediately from MIT shocks, right? You just match derivatives of these two concepts, of the MIT shock, which is just a special case of this, of our general solution. So for the size dependence, you could read off these derivatives. Oops, I don't know what happened. For the size derivatives, you can read that off from the second order derivative just with respect to a single MIT shock. And then for the history, you just do this double MIT shock thing, and then you take the cross derivative. And that's all you need to get all of these terms that are not just the size dependent terms. Okay? So already that's pretty far. Oops. Now, the big question, though, is how do we get the risk term, right? Because the risk is always the thing that we think is the hard part about this stuff, right? The risk is the part that, is the only reason why we're not just doing nonlinear MIT shocks to begin with. So for that anticipated risk term, it turns out there's a simple way to use the size dependence term to get it. And the reasoning is the following. The risk term just gives us what we call the risky steady state. The risky steady state is a concept where the shocks always realize to zero, but people still think there's going to be risk. And if you just look at our expansion in that world, where the shocks are always 0, but people think there's going to be risk, you get this half x sigma 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 squared term. You just get the risk term, right? And then if you think about the equation that this economy is solving, this F equation, remember it has a lag slot, xt minus 1, and then a current slot, xt, and then an expectation slot about future x, this thing right here. And so we can just plug these things in to the F. We say, okay, the risky steady state corresponds to where there's never any epsilon observed, where the lagged and the current is actually just the risky steady state x star, and then the anticipated effect is also x star, also the risky steady state, but now plus this other term, because when you're at date t, your expectation is still that there might be a shock. And when you take expectations, the quadratic term in tomorrow's shock doesn't go away, okay? It's still there. And so there's one more term right here, the 1/2 x sigma 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 squared, that shows up for you. And so then the risky steady state is just kind of the first order solving this steady state equation. And the way we can implement that, actually, is just by computing this from the size dependence. We already got that from MIT shocks. And then sticking this in as like a first order expectational perturbation to the steady state, and then just running our steady state code, right? So it's very, very easy to get it. You can write out also like kind of the formula of what that corresponds to, but practically that's the easiest way to get it. Calculate the size dependence. Calculate the size dependence of everything that at least shows up in a forward-looking way in the model. So in the head agent case, that means calculate the size dependence of the value function. Then stick in that size dependence of the value function as a perturbation to the expectations of everyone in the steady state. Just a constant perturbation that they always think is going to be there. That gives you the risky steady state, and the risky steady state is that additional term. So here, bottom line is we solved the quadratic MA process that gives us the full second order sequence space solution. And we've shown, and we talk about this a bit in the paper, that this perfectly agrees when we can compute both with the Prune state space second order solution. We compute 2 of the parts from MIT shock differentiation, and then 1 just by taking the size dependence from that, sticking it in as a perturbation to the steady state. And one thing I want to note about why is this so much more practical is that in the sequence space, you have to decide how far to truncate. But for this project, we found it's often practical to truncate out to an impulse of 300 periods, and then keep track of interactions with lags up to 60 periods. So that means ultimately when we write all this stuff down, we have 18,000 terms. Now there's some redundancy there, there's a little bit of symmetry, and they also vary smoothly, so you could compress it more than that, but bottom line, there's 18,000 terms. Whereas in our head agent model, it's a sort of a high dimensional head agent model, the x has dimension 5,000. So that means if you write out the whole state space law of motion, you have to show how each interaction between incoming x's leads to today's x. That's of the order of magnitude of 5,000 cubed, which is 125 billion. You can cut it in half with symmetry, but still this is something that's big enough that it barely fits on your computer, right? And if you go much further, or if you go to third order, you're not going to be able to do it, right? And that's why nobody does, second or higher order perturbation in the state space for a head agent model without somehow trying to compress the heterogeneity a lot. There's just no other way to do it. But with the sequence space, we can actually not compress the heterogeneity at all. We just keep the full heterogeneity intact and then store these terms right here.
So I thought Bandari et al. Would do something like that, or no?
Kind of. I think they take a bit more of a state space approach, but ultimately they try to compute things a lot like this. And Lon and Meyer-Gotha do too. That's like 2013 or something. So others have tried to solve for these things. I think the novel thing about the way we're doing it is that we have this certainty correspondence, so we can get it from the MIT shocks, which we think is sort of a more practical way to get it. So quickly, I'm going to talk about implications for moments. In the paper, we also talk about generalized impulse response functions, or GIRFs. So, if you want to look at the ergodic long-run mean under rational expectations, you get 2 terms. You get the risky steady state, and then you get kind of the average size dependence that happens in the model, right? On average, these are the things that move you away from the deterministic steady state. This is not a new result by us. It's also in Lon and Meyer-Gotha and also in Bandari et al., the 2 papers we just mentioned. But you can also do other things. So for instance, suppose you want the ergodic variance of the full sort of second order approximation. Well, then you get 2 terms. You get kind of the term you would just get even from the first order solution, which is often the way we calculate moments. Like this is the way I always tell students to calculate moments. Just do the first order solution and then infer the variance or covariances from that coefficient. But then we get also these other terms, interactions of the second order terms with each other, right? So we can easily compute that. It turns out that even this first order thing is accurate up to third order in sigma in this case. Now, if you want to get to higher accuracy, like formally as a perturbation of the moment, you have to add not only these terms, but some additional terms, not all the terms from our third order solution. And I'll show you how to get the third order solution in a second, but just to say, you know, with a few more terms from the third order solution that add to this, you can get a fifth order accurate approximation in sigma for any moment you want. Yep?
Are you sort of comparing this to the stochastic extended path?
We haven't done that yet. I think we should. There are some similarities to it, so I think, yeah, we should think about exactly where the overlap is, for sure, yeah. So now let's get to some applications. So first of all, I'm going to consider kind of what for us is the simplest possible shock, which is a shock, a proportional shock to income. And this emerges either from like a tax cut, or from, you know, in general equilibrium, wages changing in the model, or labor demand changing in the model. So this is not a lump sum transfer. I'll get to that later. It's a proportional shock to income that can come from many sources. And here I'm just doing PE, although we do GE in the paper. And you see here that as we, you know, change the shock size, and this is as a fraction of GDP, it says income, but it's GDP, then going up to 10% or minus 10%, you see that there is this concavity that Javier was talking about right here. First order misses the concavity, obviously, but second and then especially third order hit it perfectly, right? And this is where, you know, the smooth model is important to get those things exactly right. But then the other thing that I think is really interesting, and that Chris already kind of mentioned, right, and we've been talking about this sort of since last year when we started presenting this, is that the next period, you don't get concavity, you get convexity. Why is that? Well, those people who are pushed off the constraint, right, by the shock being so big, those kinds of people, they're not the people who are going to say, oh, now I'm going to save it forever, right? Those are the kinds of people who will typically, at least in the model, spend it fairly soon thereafter, right? You know, Chris pointed out in you know, present value terms in partial equilibrium, they'll spend everything, right? But even in just the next period or the next 2 or 3 periods, they'll spend a lot of what they didn't spend here. So we get offsetting concavity and convexity. Both cases, the third order kind of gets it perfectly here.
So Matt,
Yep.
here the transfer is targeted more towards the rich because these guys
Yes.
have higher labor income, so you
Well,
do a tax cut for everyone.
We're saying this is a tax, yes, exactly. So I agree, a lump sum transfer, or certainly a targeted transfer at the very bottom would be different. So here we're just doing the proportional thing. I'm going to get to lump sum, don't worry. So the proportional is just a really common thing that shows up not only from tax cuts, but in general equilibrium from all kinds of changes, right? Because like wages, you know, wage or labor demand changes in the typical models we write, they show up as something like this, right? So this to us is kind of the default thing that matters for all kinds of stuff that we want to look at. So you get the concavity and then the convexity. We can also apply to other things. So we can calculate the aggregate savings. So, you know, if we vary the risk sigma and then we just have this kind of one-time income shock and consider amping up the standard deviation, then the risky steady state implies, you know, higher aggregate savings. We can calculate the risky steady state. We can even calculate the entire distribution, like the entire full high-dimensional object of the risky steady state over here, and how it compares to the deterministic steady state. And, you know, we see that the whole distribution moves over to the right, right? And that's just because there's precautionary savings motives due to the aggregate risk. The entire distribution shifts over to the right. Now I want to move over to the third order certainty correspondence, because this is where things get even a little bit trickier. So continue expanding. Remember that symmetry implies that you don't get any terms with odd numbers of sigma. So you don't get these terms. You also don't get a term with 3 sigmas. So you get a cubic MA with 2 additional sources in the sum. You get first these things, which are kind of straightforward. They're just triple interactions of shocks that have been realized. And then these over here, which are interactions of sort of to first order a shock with sigma squared, with the variance of anticipated shocks, right? So this is kind of a subtle thing that gets at, you know, interaction of risk with shocks, and it captures some of the effects, for instance, that Marcus was mentioning earlier, you know, where, you know, a shock might endogenously cause effective variance to be smaller in the model. That kind of thing is captured here. So these triple interactions are kind of boring technically. They can all be obtained from 1, 2, 3 consecutive MIT shocks, kind of the same as we did the other stuff, so I'm not going to dwell on that. I'm going to talk a little bit more about this other term, right? This interaction. And this includes two effects. One is how future risk affects the first order impulse response, like knowing that there's risk affects the impulse response. And another thing is that the fact that shocks have even happened changes the size-based incidence of future shocks. And when we do all the math, we can actually prove that this term can be split into two terms which reflect sort of different parts of the perfect foresight solution. So this first term, we say, is the effect of the risky steady state on the impulse response. And we prove that you can actually get this by just doing impulse responses starting from the risky steady state, including the expectations of the risky steady state. And that's actually a common thing a lot of people do. They calculate the risky steady state, and then they do first order perturbation around that. We kind of show that that's somewhat justified, but if you want all the third order terms, that's actually not enough. There's this other set of terms. This other set of terms comes from the fact that past shocks interact with the size-dependent incidence of future shocks. It's a little bit subtle, but it's basically saying the fact that a shock has already happened kind of affects the risk going forward of future shocks, and then that shows up via expectations. And so we have a way of putting those things, which we get from the MIT shocks, right? And this isn't even a triple interaction MIT shock. This is like just an interaction of one past shock with size dependence. We get that from MIT shocks. We plug it in as an expectational perturbation now as kind of a sequence, and then we solve it using our typical sequence-based Jacobian stuff, and we can get this second term. So we can get both terms. This one's a little bit easier. This is what a lot of people already get. This is what maybe people sometimes miss. And we'll do one application of this here, which is to think about how in our model the baseline presence of risk affects the incidence of this income shock. And we show that it actually decreases the on-impact effect of the income shock. Why is that? Well, because you saved more, you had this precautionary motive because of the risks, and you put yourself in a position where you can absorb income shocks a little bit better without changing your consumption. So we have this negative term here, but then we have positive after, and it's the same sort of, snapback logic we had before. Like, people respond a little bit less on impact to an income shock because they knew there was risk that might be coming, but then they respond a little bit more in the quarters after. So when we look at the cumulative response, kind of integrating this out in a specific application, what we do is we can actually compare to the global solution, because what I'm showing you right now is a partial equilibrium household model, and for that it's possible, I mean it's not trivial, but it's possible to actually get a global solution. There's not hard GE stuff, right? So for this we have a clean global benchmark, and we can show that the global benchmark and our third order approximation are below the perfect foresight response, like a naive application of the perfect foresight impulse response that ignores risk in the cumulative consumption response. So there's something you would be missing. It's not huge here, but it's not trivial either. There's something you would be missing with the perfect foresight that our third order term picks up. And the third order term is almost on top of the global solution past 1 or 2 quarters of cumulative effect. All right? So it's pretty accurate.
How big was the income shock in this case?
In this case, I forget. I think it was 5%. 5%, yeah. So, so now just briefly looking at moments, we talked a little bit earlier about how, we can take the standard third order accurate moment from just the linear solution, or we can take the prune second order solution, calculate moments from that, or we can calculate using some third order solution information, an approximation to the moments that we can prove is fifth order accurate. And it turns out for the variance of consumption in the ergodic kind of aggregate distribution, there's no difference between using just the pruned order and then adding those extra terms for the fifth order. It's basically the same.
Can you elaborate on the pruning?
Sorry, the prune second order is just saying, sorry, I shouldn't probably say prune. This is just saying use the second order solution. I showed you the formula earlier. So this is basically what, if you looked at Andreessen et al., the prune state space paper, they have formulas for what the moments would be based on just the second space solution. And then they go to the third order solution too. That's the kind of thing that they calculate, okay? So this second order line just means take the second order solution, compute only the terms that come from that of the variance, right? And that is not a complete kind of approximation. We show that if you want a fifth order accurate approximation, there's some other terms. Turns out for the variance though, just using the second order approximation is enough to get almost everything. And then for the covariance, on the other hand, the autocovariance of consumption, just using the second order solution doesn't really get you much at all relative to the first order, you really need to include those third order terms that we can show are sort of give you the fifth order accurate, kind of fully accurate, at least if you care only up to fifth order, approximation of the autocovariance. Okay? And we have the formulas for moments and also GIRFs in the paper. Okay, so to summarize the certainty correspondence, we can obtain second and third order perturbation solutions to rational expectations models using perfect foresight methods. And I think this is like a point where, you know, I don't know, I like to stand back and say this is pretty cool, right? Because, you know, agents are forward-looking, they anticipate future aggregate risk. You might think MIT shocks are the least relevant thing in the world to this kind of concept, right? You know, and then some people, you know, people were already kind of didn't understand, right? And, you know, BKM told them, like, look, you can use this for the first order solution. But then I think a lot of people thought, oh no, that's you know, not going to work for any higher order, right? It turns out that it does work. You know, that we can get the full second and third order solution, including the risk terms, by just taking MIT shocks or taking the information from MIT shocks and using it with a little bit of extra work to compute those terms. Like, you know, in the second order, we put in size dependence as a perturbation to expectations in the steady state, and then we're there. So we like to say MIT shocks are all you need, right? That's it. What I'm going to do in the last 10 minutes is talk about validation, and then, if I have time, 2 GE applications. So first, validation. So in the paper, we have a number of different ways of validating third-order sequence-based perturbation. So, you know, we posted the paper on our website, so if you want to see, you know, you can look at these. We're going to add more in the next couple weeks. So we first compare versus third-order state-space perturbation, because we can show equivalence between our third-order solutions and the conventional pruned third-order state-space concept. And so for models like the neoclassical growth model, we've tried some other kind of classic DSG models too. On those kinds of models where you can easily calculate both, we just do both, right? And we show that they agree exactly. So we have that validation, just to make sure that our formulas are right. That's more just validating that the perturbation concept is right. And then these other two are more validating that, you know, perturbation itself gives an accurate approximation of kind of the global thing of interest. So first, we can compare to a global solution on a model where we can calculate the full global solution, which we showed, you know, was in the PE head agent model, we can calculate a full global solution, and we got pretty close. If sigma gets big enough, then we start getting further away. So there's, you know, some level of risk, a very high level of aggregate risk at which it starts failing. But for reasonable levels of aggregate risk, like I think that was 5% variance in each quarter that I showed you before, which is already a ton of aggregate risk, like much more than in reality, right? Then we can validate versus the global solution. And finally, we can validate, yep?
The second validation is also for proportional shock on income.
So here it is, yeah. So
it means that if your utility is CRA, for instance, then the shock is proportional. We end up on something similar to what Kirk presented yesterday. And so we expect the effect that was presented in the previous presentation about lambda not to be affected much.
I'm not sure if that's totally true, because these proportional shock, like, if the proportional change in income...
The Euler equation to be shifted more or less proportionally?
No, because this is a one-time shock, remember. So, sorry, each shock is a one-time shock. So it's true that if you had, like, monetary policy shocks, and this was some of the discussion earlier, those can kind of shift up your income in general equilibrium and shift everyone's Euler equations, so you don't get any nonlinearity there. If you just have like income shocks, right, like you know, that increase or decrease aggregate income by 5% every quarter, those have highly non-Ricardian effects. Like that's the kind of shock that we built like almost the entire intertemporal Keynesian cross paper about. So this, I think that's a serious test of it. There are, and I showed a few slides ago, there are some nonlinearities there. It's just that this captures the nonlinearity pretty well.
But we can still.
We can do lump sum. If you want lump sum,
to the validation,
we can add to there.
That's no problem.
We do have lump sum here, which is versus in a second, because the final validation, which I showed you some size dependence and so on, is versus nonlinear perfect foresight. And this is the kind of thing that Javier did in the paper.
But if I remember correctly, in your econometrica, when you do the tax cut, it's actually convex. So it's very different, the tax cut on labor with the lump sum transfer.
You mean in general equilibrium,
yeah.
with respect to nonlinear stuff? Yeah, there's some forces, I think, that maybe make it convex when we did the global thing there. Here I'm just going to do partial equilibrium to match up better with what you did. So far we showed versus nonlinear perfect foresight. So just ignore the risk terms, just see how well it captures the perfect foresight part. So far we just did the proportional income shocks. But you might be asking, Javier just showed that, we don't think it matches nonlinear perfect foresight very well. So, how do we reconcile these two papers? I don't think it's that the calibrations are that different, because actually they're both kind of, in many ways, state-of-the-art kinds of calibrations at kind of a high level. So that's not what's causing it. I'm going to say there's several things that are causing it. So first, there's the issue of, are we having a smooth enough model to get the second and third derivatives, right? So, that's an issue that I think I showed, numerical differentiation or analytical, it can be very troublesome if you don't have kind of smoothness properly implemented. So that's something that can affect the second and third order accuracy. But then there's the more basic question of first order versus perfect foresight. And so indeed, when we do a one-time lump sum transfer, like in Javier and Greg's paper, we do get here, you can see, sorry if the colors are faded a little bit, you can see that, first order massively overshoots, and perfect foresight is fairly concave here, right? And then second and third order, they help for a while, especially second order, but past about a size like 4% of GDP lump sum shock, which is actually a very big lump sum shock empirically, by the way. Past about 4% of GDP, it stops doing as well. So this is genuinely something where we get a fairly big nonlinearity, and even second and third order can't help us, right? But what if we're interested not just in the impact effect, but because we knew that convexity offsets things a little bit, in an effect over a slightly longer period of time? At least here, we show, over the first year, it's shockingly linear, right? And there's a nonlinearity, but the second and third order deal with that pretty well. I wish I had, the thing over just 2 quarters or 3 quarters, because there it's more nonlinear, but still, the second and third order deal with it pretty well. So it's really that you have to have a lump sum transfer, number one. It has to be big. Number two, you have to just care about the income effect, not the effect over like 2 or 3 periods. That's number 3. And then number 4, it has to be a kind of shock that's not persistent, right? It has to be like a total one-off, right? Which maybe for a regular stimulus check is true, but when we're thinking about such big shocks, it's often we're thinking about something other than just a regular stimulus check. So over here we add persistent 0.7, and we show actually then even the impact effect is pretty linear, and again the second and third order do a very good job, right? So 4 things. It has to be a lump sum transfer, it has to be big, it has to be, you're looking at the one-time effect, not a cumulative effect over a few quarters, and it has to be non-persistent for there to be this failure of second and third order.
So just
Yep.
understand the last result. Is it because if the shock is permanent, then you don't move people off the constraint?
That's basically the intuition. So
I can
yes.
think about at the end what matters to understand whether this works or not is if a lot of people move away from the constraint
Right.
or not.
So when you give them a one-time shock in one period, it's a very jagged thing, right? Where they're not getting it in the future, right? So they want to smooth at some point. But if you're going to give them something next quarter or the quarter after that, then it's not as jagged. And what's interesting is it's actually cumulatively a much bigger shock. You're giving them a lot more money. But because it's spread out, not just all a bullet in one period, then it's not nearly as nonlinear. So, but of course, the first thing I mentioned was just size, right? So that got us to think, what is like the biggest possible shock we can think of? So we went and looked at the data, asked the biggest increase in the deficit over potential GDP in the quarterly national accounts ever. And sure enough, it was COVID, right? It was 20%, right? 20% in one quarter, the deficit went up. Now, we're not trying to make a model of COVID, because as many people pointed out, like Gianluca, there's other things going on in COVID or even in a recession. We're just using this as like a biggest possible shock benchmark, right? Like how big can a shock reasonably be? So we kind of smooth it out to get a stylized benchmark that's, it's almost a perfect nonlinear least squares fit. It starts at 20% of GDP, and then it goes down 0.7 per quarter. So when we do that, we have to decide how to map it onto a lump sum shock or a proportional tax cut shock or a proportional income shock in our model, right? So if it's a lump sum, it doesn't work quite as well, although it still works decently. We have that in the paper. But, not all of this deficit was like stimulus checks, right? It was a mix of many things, including aid to firms, lots of stuff that is not in the model but might correspond more to a proportional income increase, or just making sure our incomes could be sustained, right? So for our baseline here, we take a shock that's this giant with this persistence, and we say half of it, 10% of GDP, is a lump sum transfer, and 10% of GDP is a proportional income increase. And we do that mix. And we ask how well can third order approximate it? And the answer is, I mean, if you could really zoom in with your eyes there, you see it's not perfect, but it's very close to being perfect. And if you look cumulatively over a couple quarters, then it's perfect, right? So we think this is kind of the biggest possible shock. You'll note that, Greg and Javier have kind of like an unconventional normalization. They express everything with respect to annual GDP, even if it's a one-quarter shock. So in their convention, this is only a 5% shock, right? And then their 15% shock, which is the right edge of their axis, is a 60% shock out of GDP, which is 3 times bigger than the biggest thing that has ever happened. So some of this is a scale thing, but we think this is a good representation of the biggest shock you can possibly get. And if we don't think of it as all lump sum, then actually third order does a pretty good job. All right, so I have probably like 1 minute. So let me just say, we have 2 quantitative applications. First of all, we have a full Hank model, and we show how kind of infinitesimal fiscal multipliers over the ergodic distribution vary. And we find that they actually vary quite a bit in the second and third order solutions, and that when output is higher, the fiscal multiplier is quite a bit lower. We also have a menu cost model, the Phillips curve. Our findings there are very consistent with lots of people in that literature, but we're able to use our perturbation machinery. So we show, for instance, that there's a non-trivial increase in Phillips curve slope when inflation is high. Not a new result, of course, just something that shows off how far this machinery can go. And so, to conclude, we have a fairly simple message, which is that MIT shocks, assuming that you have a smooth model that's properly differentiable, are all you need to get an often very accurate higher order perturbation representation of the economy. Thanks.
Is it fair to say that at least right now with the current implementation, one limitation of the method is that we wouldn't be able to deal at least perfectly with like zero
No, that is absolutely true.
capacity constraints, because
Yeah, so I think
constraints at the aggregate level that make the approximation at the
perfect. Yeah, so I think one important message here is generally you do need smoothness, and so we need to, for instance, smooth out with smooth shocks which you think exist in the world, all the kinks at the individual level. But if you have a harsh, non-smooth aggregate constraint like the ZLB, then you can't do this. So that is definitely a limitation. Great.
Okay, so I think now we have a break and we meet at 3 p.m.
No, we were having and I mean, smoothing aggregate nominal wage, right?
Yeah, of course. Yeah. issue.
Thank you for sticking around. We're excited to continue with an odd approximation of inflation for state-dependent pricing models.
Thank you for having me. Thank you for putting the paper in the program. This is joint work with the usual team, Mark, Simona, and Yoris, and Madi, who is a brilliant PhD student at NYU. Simona and Yoris are at the New York Fed and Bank of Belgium, respectively, so the usual disclaimer applies. So I'm going to start the presentation with some data. Here I'm showing in the top the panel for the United States, bottom for the Euro area. This is a plot that in some form or another you might have seen already. It has motivated a resurgence in attention to state dependence and menu cost models. The red line is CPI inflation. The blue line is the frequency of price adjustment, which is calculated as the fraction of firms that changes their prices within a quarter. So as you can see, for the first 20 years of the 2000s, we had a long period, an extended period of low and stable inflation, and the frequency was also low and stable, perhaps with the exception of the financial crisis in 2008 in the United States. And then after COVID, we had this inflation surge that everybody's aware of. In the United States, year-over-year inflation went above 7%. In Europe, it touched approximately 10%. And this is associated with a steep, extremely large increase in the frequency of price adjustment. And so a lot of people, including myself with the same team in the previous work, we have been thinking about the movement, the correlated movements between inflation and frequency through the lenses of state-dependent pricing. And in particular, in the previous paper, we showed using Belgian data on prices and cost, that once you calibrate and discipline a state-dependent model using this information on cost, you can actually explain very well the movements in the inflation and frequency, both pre-pandemic and post-pandemic. But some of the issues that we have encountered working with this class of model is that they're analytically and algebraically not so easy to track. In particular, they don't admit a closed form solution. It requires typically using computationally intensive methods such as global method, except for if you have third order approximation as they show today. And more deeply, there is a critique that has been raised recently by Ben Moll and co-authors regarding the fact that once you introduce a strategic complementarities in this class of model, firms, when they are setting their price, they need to take into account and forecast the evolution of the entire distribution going forward. And this might be perhaps a little bit too much to ask for the rationality of agents in reality. So we're going to attack this problem by proposing an algebraic approach, a closed form solution to this class of model, which is going to deliver in practice characterization of the entire impulse response function of inflation. So compared to the work of Fernando and Francesco, which characterized the cumulative impulse response, we're going to characterize the impulse response point by point over time. And this takes the form of a cubic, this is where the title comes from, odd polynomial in a single number, the mean of the distribution of price gaps. And of course, we're collapsing the entire information on the distribution in a single number and characterizing when this works and when it doesn't. And to the extent that it works, this provides a tractable and a computationally simple tool that we're eventually going to put into Dynar, combined with the richer DSG model, do estimation, filtering, smoothing, and this type of rich exercises that with global methods will be quite challenging to do. And to address Ben's critique, the fact that firms in the model will only need to keep track of a single number provides a quasi-aggregation result that relaxes the toll on rational expectations. Now let me go through the plan of the talk. I'm going to start from the theory, describe the model as quickly as I can. Hopefully it won't take too much time. Then go into the details of the characterization of the impulse response and then do quantitative exercises. Okay, sketch of the model just in words. And then I'm going to go through some of the equations. So this is frontier, I would say, menu cost model, in which there is a continuum of monopolistically competitive firms. They are subject to heterogeneous shocks. For today's talk, I'm going to restrict the attention to Cobb-Douglas price index. In the paper, we do Kimball, which Nessie has a special case. This will come with an additional approximation error, which I won't abstract from today. We're going to introduce instead strategic complementarities by having curvature in the production function. We're going to allow for decreasing returns to scale. And I'm going to consider a loss function for the firm, which is quadratic. This potentially comes with an approximation error as well, which we characterize in the paper, but I'm going to abstract from that as well today. Firms choose prices and adjust prices subject to a fixed cost, which is drawn from a distribution. So this is the random menu cost that was introduced, I believe, by Cavalier and Engel. And on top of that, we're going to allow for the probability that a free price adjustment occurs, as in the Calvo Plus model of Nakamura and Steinson. Today's presentation, in the theory, I'm going to go without any discussion, assuming no trend inflation. We show that we can characterize the impulse response for any level of inflation still in an algebraic way. And in the quantitative exercise, I'm going to bring it back, but for the theory, I'm just going to abstract from it. And then the fundamental of the model will be marginal cost. At the beginning of the presentation, that will be exogenous. Then when I put the pricing block into the full GE, I will endogenize that with the new Keynesian demand block. So let me start discussing a little bit more in detail the model. The primitive of the firm is nominal marginal cost. Here, for the moment, you can think of that as being exogenous, and then later I will make it endogenous when I put it together with the determination of wages in G. Marginal cost is decomposed into three components. One is aggregate component, XIT. Let me see, how do I highlight? Yeah, I guess I'm not highlighting. Aggregate component XIT. The only restriction that we are making is that this is Markov. A firm-specific idiosyncratic shock, you can think of that as a firm-specific TFP shock. We're going to assume that this follows a random walk. I will use this assumption in the next slide. And then the shocks are distributed with a symmetric distribution, and we can relax that to leptokurtic shocks. Decreasing return to scale, so when nu is equal to 0, that will be constant return to scale. Nu positive is decreasing return to scale. Now, take a model in which there are no nominal rigidity, so prices are fully flexible. What would like firms to set their price to? They would like to set the price equal to marginal cost. But now I'm going to replace for output of the firm the demand curve under the Cobb-Douglas price index. And you see that there is P0 on both sides, so I'm going to rearrange and divide by the coefficients, obtaining that if there is no nominal rigidity whatsoever, the target price that the firm would like to set is a linear combination between the exogenous component of marginal cost and the price index of the economy. Okay, and so this is where strategic complementarities come into place. Whenever a firm wants to set their price, they need to know what the aggregate price index is, and to do that, they need to evaluate the entire distribution of prices.
It's not the aggregate.
The PT? That one is the aggregate one. So I moved from the firm level one, which has a half F. I replaced the demand curve. So YT here without the F is the shifter, and then rearrange, and the component there is the aggregate one. You need to know that too, exactly. But everything eventually will be endogenous there. And so also XIT will depend on YT. They will be both functions of the aggregate later. So what's the problem of the firm? They choose the price that is set conditional on adjusting, and whether to adjust or not. This is an indicator function that takes value 1 if they adjust, to maximize the expected discounted present value of quadratic losses minus the menu cost that they pay if they adjust. So quadratic losses are the distance between the price that they have and the static target price. B is a number that is positive. And the menu cost that they pay is this random variable KTF, which is paid whenever the indicator function takes value 1, and KTF is drawn from a distribution G. It's a parameter itself. It's a number, yeah. We estimated that in previous work. It's like 0.5. Okay, so this first order condition for this problem is standard looking, especially if you're familiar with Calvo. So the price that the firms would like to set is the present discounted value of current and future static target prices. Now, what's inside of this, the discounting the firms are using to calculate this present value? Well, of course, there is beta, the time discounting, as well as the probability that they adjust between any consecutive period. Now, the probability here is captured by the indicator function. So, for example, if 3 periods from now, firms know I'm going to adjust with probability 1, then anything that happens after that is completely discarded and doesn't enter the calculation for the price today. Now, I'm going to do, so this characterizes, if you want, the intensive margin. So now I'm going to think about the extensive margin of adjustment from the perspective of firm. So here we're going to do a small deviation from what the literature typically does. So typically what the literature does is that they define a state variable, and they show that it is a valid state variable, which is a price gap, the difference between the static target and the price that the firm has entering the period. This is what enters the profit function that I showed in the previous slide. So instead here, I'm going to leverage the optimality principle to define a new state variable, which then I'm going to use to characterize the extensive margin. So this new state variable is the distance between the dynamic price the firm would like to set, which was characterizing the first order condition in the previous slide, and the price that the firm has entering the period. I can, in terms of this state variable, construct the indirect value function of not adjusting, which is equal to, inside of the profit, the quadratic profit, I'm adding and subtracting P star, and then I'm computing the expected value of the continuation conditional on this new state variable. So basically, what have I done? I'm plotting this value function on the right. I'm shifting the value function around 0. I'm recentering so that when a firm is setting price, because it's set exactly equal to P star at the optimum, the value function is maximized at 0. Okay, so it's just a horizontal shift of the value function. Now, the distance between P0 and P star, this xt star, does not have an F subscript. So this is common across firms. Why? Because idiosyncratic shocks are random walk. So in the present value, they cancel with the contemporaneous one. This is a standard trick that we use in the literature. But in any case, I'm changing state variable, and the state variable that I'm using is this dynamic price gap. Why am I going to do that? I'm going to show you in a couple of slides. But as a function of this new state variable, I want to characterize the probability that the firms adjust between any two consecutive periods. So this is the expectation of the indicator function conditional on their state. Okay? And then I'm going to leverage the assumptions of the model. So with some probability, you get a free price adjustment, HT0. With a complementary probability, you adjust only if the value of adjusting, V of 0, is larger than the value of not adjusting, according to the distribution of the menu cost, which is G. Okay? Now, what's the plot of this function is the one on the right. So on the x-axis, I have the state variable that I'm drawing. The hazard is minimized exactly at 0. Why? Because if you are at the optimum, that's when the probability of readjusting is minimal. And then it increases in a convex way, and at some point it becomes flat because it touches 1. And this is very general. The fact that it's minimized at the optimum is convex around that. It's very general. It depends on very weak assumptions. And so, because of these patterns, we can characterize it quite accurately with a local Taylor expansion around the reset point. So basically, because it's convex and minimized at 0, it's well approximated by a parabola that does not have first order term. So it's a doesn't have to be. But for general G, it will not be typically symmetric, but yet this feature that is minimized at the optimum and is convex around the optimum will be generally true, and so the quadratic approximation locally will be accurate. Now, remember this notation, so there is HT0, this is the intercept of the hazard, this is the free adjustment parameter, and the other piece of notation to remember is phi, which is the curvature of this GHF.
Just to keep back your assumption, so here if you had trend inflation in the primitive model, that thing would still work? Or you have
Yeah, it will still work. Precisely because of the way we have defined this new state variable, which will include the trend. Exactly. What will change with trend inflation is that it's not obvious that the first derivative will still be 0. So that will be different. But we can characterize it in closed form, and we do that in the paper. Good? So we have this quadratic formula in our pocket. Now let me illustrate with a plot what happens in response to an aggregate shock. So far I characterized the problem of one firm. So now let me introduce the entire distribution. In the background there is idiosyncratic shocks. Everybody is centered around this reset point of 0. So I'm plotting here the distribution overlaid by the GHF. The region that is in red is above the GHF, tells me the mass of firms that is not adjusting prices. The region below tells me the mass or the probability in the aggregate of firms that is adjusting prices. Now what happens with an aggregate shock? Well, on impact, the distribution just shifts to the right. This is very intuitive because the aggregate shock is shifting everybody by the same amount. But this is changing quite a bit of the fraction of firms that is adjusting prices versus those that are not adjusting. In particular, many more firms will start adjusting prices. So the distribution shifts to the right, the average shifts to the right. But then because I'm working in discrete time, within the period, some of the firms will start immediately adjusting, and so the distribution will change further shape. It will converge, we will move again back to the left, the average price gap will again move to the left, and now the variance, the distribution will become flatter because some of the firms are adjusting, some of the firms are not adjusting, and so the variance goes up. Now remember these pieces of notation, xt without the f is the average gap, with the f is the firm level gap, and the cross-sectional variance is sigma t. Now let's get to the meat. This is the derivation of the odd approximation. So because of the Cobb-Douglas price index, what's the definition of inflation? Is the, and the large number, it's the integral of the probability that the firms adjust times by how much they adjust, conditional on adjusting, according to the distribution after the shock. And you see now why I have transformed the problem in terms of the new value function, because h is a function of x, and so this entire integrand is a function of the same variable. Now let me plug into the quadratic approximation for the hazard that I told you before about, and on the right hand side I'm plotting the integrand. So in the menu cost model, the integrand just coming from the quadratic hazard is a linear term that multiplies the free adjustment frequency times the curvature of the GHF and the cubic function of the firm level gap. On the other hand, in Calvo, the frequency will be a constant, and in particular it will be the free adjustment parameter plus the curvature times the variance at the steady state. So that will be the steady state frequency of price adjustment times a linear term, times the firm level gap. So what does it mean to compute inflation? It means to integrate the red curve with respect to the distribution that is shifted by the aggregate shock. So this is what I'm doing in the first step 1. Now, in step 2, I'm going to use the algebraic intuition that I was mentioning in the beginning. So this is the expansion of moments. So the integral of x tf to the third power with respect to the distribution is the cube of the average gap plus 3 times the average gaps times the variance. And there is also a skewness term here, which I'm abstracting from, but in a paper we have that. Now, this is just using expansion of moments, but is already giving us a representation of inflation in which there is a linear term that multiplies a term that depends on the variance post-shock, and the cubic term that depends just on the curvature of the GHF. So what's the last step? Let's approximate the variance as a function of the aggregate shock. And because of all the symmetry properties that I have here, the displacement of the variance to a first order will be equal to 0. The movement in the variance will depend only on the quadratic displacement of the average gap multiplied by the curvature of this approximation. Now, it takes quite a bit of work to characterize all these coefficients in closed form as a function of parameters, but we can. We can exactly characterize how sigma moves with the aggregate shocks in closed form in this model. And so this leads to the odd approximation, which is the main result of this paper, in which inflation depends as a coefficient times the first moment of the gap distribution plus another coefficient times the third moment, so the cube of the first moment of the price gap distribution. And the linear coefficient depends on the steady state variance, and the cubic displacement depends on how the variance responds to the aggregate shock.
So can I just ask, so this is both kind of perturbation in the sense in the last lecture, or in my talk, right, with respect to aggregate variation, and then there's also a distributional approximation? It's kind of both of those?
So we're approximating the variance with respect to aggregate shock, yes. Yeah, so there are two pieces of approximation. One is at the firm level, the GHF. So this is an approximation firm by firm, and then we're keeping track of the integral of those errors. And then there is a second layer of approximation, so that takes you to step 2. And then we want to deal with the movement in the variance in response to aggregate shocks, and that's another layer of approximation, and that's at the aggregate level. So a piece of approximation at the firm and another approximation at the aggregate level.
It would be useful to state it in terms of, okay, you have a primitive loading on linear model, and then you're going to take Selton sigmas to 0.
Yeah.
Different things.
So this is this.
Kind of show, like, does the order matter, or
Yeah. So this is what we do in this theorem. So I'm going to abstract from non-stationary environment. I'm going to drop the t subscript from the value function. And then I'm going to consider an aggregate shock of size delta. I'm going to keep track of the response of the average of the distribution, and I'm going to call that x of delta. I'm going to show you later exactly how to keep track of the average. Now, we can characterize in closed form the impulse response function of the frequency to a second order and inflation to a third order by keeping track of the average price gap response, x of delta. And in particular, the frequency will be a quadratic function of the average price gap, and inflation will be a cubic function with no quadratic term under our symmetry assumptions. And so, to the extent that you can keep track of the average gap, you have the full impulse response of h and pi. And then, to characterize x, once you have this, is just a Deinar code in which all these equations are linked.
So here it looks like you're thinking of an MIT shock inside delta.
This is, yeah.
You have sort of the aggregate risk coming. Like, you don't have this precautionary pricing thing from, like, there's risk to marginal costs.
So this is an...
But then feedback, like, that's not there.
So this is literally this type of... So we start from a stochastic steady state, and we shift the entire distribution horizontally. So I think because we start from a stochastic steady state, there is risk in this.
But you mean by stochastic steady state is the risk that comes from the idiosyncratic?
Yeah.
So it's idiosyncratic,
Yeah.
but not the aggregate chance.
That's right. That's right.
Like in your model with
I see.
complementarities, you have risk that comes from aggregate movements in costs, that
Yeah.
all the y or whatever, and then that's feeding in.
Yeah, that precautionary risk, I don't think it will be in the steady state. That's right. That's right. I mean, maybe there is a simple way of doing that. I will have to try to work out the math. Okay, but anyway, we're characterizing the impulse response of frequency and deflation, and now let me quickly decompose it into different pieces. This is going to come in later when I do some plots and decomposition. So you can decompose inflation into a Calvo term, a frequency term, and a selection term. This is kind of similar to, related to your paper on the decomposition of a menu cost model into two time-dependent models. So there is a Calvo component, which is the steady state, so the intercept of the frequency times a linear term. There is the displacement that is due to the frequency, that's specifically third order in the average gap. And then there is everything else, which is selection. And so something that I find extremely interesting here is that typically we think about selection as the covariance between the hazard and the gaps. And we think about that as a higher order term, but it's not. There is a first order effect of the selection itself. So if you want, the covariance between hazard and gaps affects inflation to a first order. And then there is a higher order term as well. Good, so what did we do so far? We showed how, so we started from a model in which in principle you have to keep track of the entire distribution. This is particularly complicated because the distribution is infinitely dimensional, the law of motion is nonlinear, it's complicated. Moreover, we've been thinking really about a mean field gain fixed point in which the decision of a firm to adjust prices depends on the evolution of the aggregate price, but the evolution of the aggregate price depends on the decisions of the firm, and so this is a fixed point between a forward-looking equation and the Fokker-Planck, which is backward-looking. Moreover, I'm going to soon nest this entire model into GE, and so I'm going to make marginal cost be endogenous. And these three difficulties make global methods quite costly, and in particular, if you want to go into estimation, filtering, and some type of complicated counterfactuals, this makes the problem quite complicated. In this paper, we collapsed the information of the distribution into a single number, single scalar, which allows to do standard perturbation methods. And in the paper, we discussed how to do extension with trend inflation, skewness, leptokurtic shocks, and non-stationary environments.
It's cool that you can get some traction here, but does the first order, that you just did the first order?
I'll show you the second part of the presentation is all about showing that when it matters. Exactly. So let me close down the model. I've described so far the pricing block. There is a bunch of equations there that I'm going to discuss a little bit more, but definition of price gap, definition of the price level, the static target. Before it was a function of marginal cost, and now when I add the new Keynesian block, there is the forward-looking standard aggregate demand curve and the Taylor rule. So there will be a feedback between the aggregate demand and marginal cost, which shows up in the static target that a firm would like to set conditional adjusting. Yes?
So given this general equilibrium closure, maybe return to like the previous questions about the interpretation of what exactly is being solved for here, in the sense that if I would do a conventional kind of perturbation, second, third order, and in the aggregate shock process, I would have, nonlinearities in all parts of the model, right? I guess here are we saying we believe they're just much more important in the pricing block, so that's what we want to capture, and we're happy to do the first order and everything else?
So here I'm isolating those nonlinearities from the pricing block to make a proof of concept. If you believe that the nonlinearities from the aggregate demand block are super key, you can have them here, and you will need to tackle them in perhaps a different way, maybe doing perturbation methods also there. So here I'm isolating the nonlinearities that come from the movement in the frequency. I will argue that this seems to be explaining quite well what happened during the inflation surge, but that might be specific to.
It's just somewhat tricky to interpret what exactly is being recovered in something, because we have like the usual guarantees of what like perturbation or like overall shock volatilities is recovered.
Yeah.
Right? And here we're kind of doing it in one part of the model and not another one.
I mean, it's not obvious how much the nonlinearities, let's say, in aggregate demand contribute. This is a method, if you want. So, like, if you really think that those nonlinearities are important, you can add higher order terms into demand. Exactly. In this model here, it will be less important. This is the Gabay discounting. Yeah, just yeah. Yeah. But exactly, so like in a Hank model, that would be really important, so you might want to take that into account. Okay, and second thing I want to show. So what's the Phillips curve in this model? It's ugly, but you can derive it. It's a combination between the three equations that I have here. So price gap, the formula for inflation, as well as the forward-looking formula for the reset price. So before I show you that the reset price is the present discounted value of current and future static targets, when you write it recursively, it looks like this. And this is exact under some assumptions on the shocks. Finally, what's the role of trend inflation? Well, it changes the formulas a little bit. It adds a quadratic contribution to inflation and a linear contribution to the frequency. And we can characterize that in a closed form as well. Three shocks: cost push, demand, money. Demand enters the aggregate demand block. Cost push enters the static target, money the Taylor rule. Good. Questions about the model? Good. So let me do some warm-up first. I'm gonna show that it is a good approximation. So we're gonna solve the model fully non-linearly in the pricing block, but still assuming linearity in the aggregate demand block. And then we do like global methods, value function iterations. And I'm gonna plot the impulse response of the global model compared to the impulse response of this approximate menu cost model for four variables: inflation, frequency, output, nominal rate, for small shock, medium shock, large shocks. So as you can see, the black line and blue line overlap quite well, indicating that for any size of shock, this is a good approximation. Calvo reacts less. This is kind of by construction. So here it's an initial partial answer to your question, Adrian, which is that for large shock, the nonlinearities will bite in. In this case, the Calvo model reacts less. For small shock, they are kind of overlapping. Now, let me go into the interesting part. So I'm going to be talking about, I'm going to do,
What did you calibrate this?
we recalibrate the Calvo so that, yeah, so that it hits the, yeah. Let's do historical decomposition. I'm going to be matching inflation, real output growth, and policy rate, in particular the shadow rate, for the period 2000 to 2025. And then I'm going to estimate the parameters of the Phillips curve and the frequency in two stages. So stage one, I do a first order Kalman. So why am I doing this? Following the work of Jesus and Borogan and Luigi. So when you do estimation at third order, some of the moments might not be very informative and the likelihood becomes very flat, so you have to be a little bit creative. The way in which we are being creative is to a first pass, we estimate a first order Kalman filter and we estimate the coefficient that pertain to the first order variables, the first order displacements. So those are linear displacement in the hazard and linear displacement in inflation and the shock persistence variance measurement error. Then to a second stage, we simulate the path of the state variable using a third order particle filter. And then we're gonna estimate the parameters that pertain to the nonlinearities of the model by targeting specifically the inflation surge in 2019, 2023. Okay? Then once we have all the parameters, we do particle filter smoothing, we recover the full shock, history of shocks with the backward pass. This is what we get. So top panel is United States, bottom panel is Euro area. What I want to convey with this graph is that the shocks that we're getting are quite reasonable. Let's look at the US, most of the variation in normal times in inflation is like demand shock. In 2015, there was an important role for negative cost push shock, kind of in line with the narrative that oil prices was reasonably low. During COVID, we're picking up demand shock. During the inflation surge, it's like a split between cost push shock and money shock. This is consistent with the oil prices going up and the Fed reacting a little bit slow to the surge. And then by the end, when the tightening comes into place, money shock become less important and demand starts picking up. So a reasonable shock. Now let me focus a little bit more into what the third order is doing. So here I'm plotting cost push, first line, money, and demand in the third line. In dark dashed gray is the first order shocks. In red is the particle filter third order shock. So what you can see, especially if you look at the circles, throughout the entire period, the variance to the third order of the cost push shock is smaller. So there is a shock compression, a reduction in the importance, if you want, of the cost push shocks. Why? Because cost push shocks and the nonlinearities kind of speak to the same fluctuations in inflation and frequency. So if you want, by modeling endogenously the nonlinearities, we're removing some of the role to the cost push shocks, which are ex ante a little bit of a black box for some of us. On the other hand, monetary policy, monetary innovations kind of don't change too much. And demand innovation, if anything, they gain a little bit of contribution. They are more volatile to a third order than to a first order. So there is shock compression when it comes to cost push shock, and a little bit of shift in weight from cost push to demand innovation when you move from first order to third order.
So, and then the interpretation for that shift in weight is just that now, like, your demand shocks are going to propagate like they would in a model without the nonlinearity plus the endogenous cost push shock.
I think.
So then, like, the baseline, like a fully linear estimation, would just then need to load that kind of co-movement on the cost push shock. Well, now, like,
yeah,
right?
There is more endogenous propagation. That's the way I'm thinking about it. If you can say that demand shocks are a more interpretable shock than the cost push.
Shock in your model is going to have the same IRFs as a demand shock in a linear model plus a sequence of cost push shocks.
Right. That's exactly what's happening. Correct. So speaking to your question from before, here I'm doing the decomposition into Calvo term, which is just the linear term, and then selection and frequency. So in normal times, Calvo is explaining the vast majority of inflation. And then during the inflation surge, actually the nonlinearities are quite important. Like for the US, they explain, how much is that? Like almost 2% of inflation. For the euro area, this is a lot. This is like 4% of inflation that comes from the nonlinearities of the menu cost model. I can plot the slope of the Phillips curve. There is a clear notion in this model. This is the derivative of pi with respect to the state variable x. As you can see, the slope becomes steeper during the inflation surge in both Euro and United States. Interestingly, it goes up quite a bit also during the financial crisis. It was negative inflation consistent with the frequency going down, as we saw in the data. And then I'm plotting here the plots of the frequency in the model against the frequency in the data, which is untargeted. So for Euro area, I think we're doing great. We're matching the frequency. For the United States, I think the behavior of the frequency during the financial crisis is reasonable. During 2021, we're getting a big spike in the model, which generates a lot of nonlinearities. There is something that happens in the data that is very difficult to explain, like a 20% increase in the frequency maybe is due to like firm switching to online instead of, and so prices becoming more flexible. So there is something in the data that is really difficult to capture, but even for a smaller movement in the frequency, we're getting a lot of nonlinearities induction in the inflation, the real variables. Good. So in the last, how much time do I have?
12 minutes now. 11.
Okay, so I have a little bit of time for questions. In the last 10 minutes, I'm going to speak about two policy exercises. So the first one is to highlight the acceleration of inflation that comes from having the nonlinearities inside of the model. So what I'm doing here is that I recover the shocks from the historical decomposition, and then I'm gonna feed into the model the cost push shock and the demand shock, shutting off the money shock. So this is answering the question, what would have happened to inflation according to the ex-post historical decomposition if monetary policy had followed exactly a Taylor rule with coefficient 1.5. And so as you can see from the first panel, both in the United States and in Europe, the nonlinearities are generating quite a bit of a spike in inflation. In particular, there is more than 1% extra inflation in the United States, and for Europe this is massive, this is like 3 percentage points. So this is due to the movements in the frequency, and you don't actually see much extra movement in output. This is reasonably surprising. But so the bottom line of this graph is from the perspective of a firm, from the perspective of the central bank that was sitting at the beginning of, the end of COVID, the beginning of the inflation surge, and using a Calvo model to forecast the effect of oil price shock, they would have missed, it's intuitive that they would have missed quite a bit of the inflation surge, and so perhaps this can rationalize why they started tightening in late 21 and not at the beginning of the surge. We're calibrating the Phillips curve to be quite steep, yeah. Like the slope that we have should be like 3%, I think, more or less.
So basically in those periods of more inflation doesn't have any impact on output.
Yeah, yeah. I need to do the back of the envelope calculations for the slope of, okay. This is the slope of the Phillips curve in the space of pi equals to slope times x. So this is if you want a reduced form slope for the Phillips curve. In that period, the frequency went up quite a lot, increasing the steepness of the slope, and that explains why output didn't move too much. Yeah. Okay. So last exercise, and then I'm gonna conclude with this slide. This is also a nice connection with the next paper by Peter. So what we're doing here is that we are asking how much of output in terms of percentage point of inflation does the Fed would have, or the European Central Bank would have to give up in order to move from accommodation to tight monetary policy. So we're calculating sacrifice ratios. Let me explain in detail what this exercise is. So we simulate the entire model under an accommodative policy rule. So phi is equal to 1.01. We recover the shocks. We have money, cost push, and demand. We shut down the money shock as we did before. So we're saying, suppose that the monetary policy is following exactly an accommodative Taylor rule. We feed into the model cost push and demand, and we are getting the path of inflation. So this is the blue dashed line that you see in the first graph, in the first column of the graphs. And then we say, now let's calibrate the model to match Calvo. Okay, so we recalibrate the model to match Calvo. We bump up the cost push shocks so that the Calvo model matches under accommodative policy exactly the same inflation path as the menu cost model. So of course, because Calvo is less reactive to shock, we need to feed into the model bigger shocks so that the accommodative, under accommodation, the inflation path is the same in the two calibrations. Okay, so now we have a counterfactual path and sequence of shocks for both the menu cost model and the Calvo model under accommodation. And what we do is that we increase the Taylor rule parameter for both models, and we see what would have happened in both cases. As you can see, of course, you're moving into tight monetary policy, and so inflation goes down, and the output goes down as well. But by how much? You can see that in Calvo, there is less reduction in, so there is, inflation goes down by less compared to menu cost model. This is intuitive because by moving from accommodation into a tight monetary policy regime, you are killing the endogenous feedback and the nonlinearities in the endogenous inflation accelerator. So the response of inflation under the menu cost model is larger than it would have been under the Calvo model. Surprisingly, this comes at smaller output losses. In particular, you can see that the red line for output lies below the blue line for menu cost. And so this is signaling that to move from accommodation to a tight monetary policy in a world that is non-linear, it is less costly than in a world that it is linear. You can visualize this in terms of sacrifice ratio, so how many percentage points of output over inflation you lose by moving from accommodation to tight. For Calvo, it's about 2.5 percentage points in the United States. For the euro area, this is about 5 percentage points. In blue, I'm showing the same line for the menu cost model, which is not a constant anymore because the derivatives are nonlinear. And you can see that it is uniformly lower, so it is in general attacking inflation more aggressively is typically easier under the menu cost model because you kill the acceleration, but it becomes particularly valuable in moments in which inflation is the highest and the sacrifice ratio is the lowest. And during the 2022 inflation peak for the United States, the sacrifice ratio decreases by approximately 0.5 percentage point, whereas for the euro area, it cuts in half. So that's a massive massively easier to move from accommodation to tightening at the peak of the inflation surge if the world is nonlinear.
What if I try to go all the way to perfect inflation stabilization, which here I guess the central bank can be doing, then you're going to just see a difference in output that's coming from the difference in the inferred cost push sequences. So that's
right.
That's what it, okay.
That's what it will happen. So you will get even larger output losses, and you will get this to an extreme way in which menu cost Calvo will predict an extremely large output loss to stabilize that inflation surge, whereas menu cost will predict a larger than this output loss, but smaller than Calvo.
What I'm wondering is just, I mean, how extreme it would be on the Calvo side, because basically once you would just be showing us what the estimated cost push shocks are, right?
Yeah.
That would be the difference across the two, because in both cases you perfectly stabilized inflation.
That's a good way of visualizing. Yeah, I don't have that plot in here, but so yeah, so this kind of sets up the stage for Peter, who's going to talk about striking the iron when it's hot. And so this plot is kind of aligned with that. It's saying that it is easier for in terms of trade-off between inflation and output for the monetary policy to stabilize inflation precisely when the nonlinearities are kicking in, which is at the peak of the inflation surge. Okay? I conclude with this slide, so if you have more questions, please, this is the moment. Right.
It would be nice to compare it to yours to see, how would they stack up.
Right. So in the so basically there is, even in their world, there is a quadratic approximation of the hazard. I think up to a relabeling, some of the things might be equivalent. I think so. We're going in slightly different ways. So the way they're going is that they're taking the canonical menu cost, so they impose additional structure to deliver the result. Here we're saying, okay, let's zoom out for a second. Let's just think about what's the key feature of the model, which is the fact that the hazard at the optimum is a convex function and is minimized. Once you take, which is true for a large class of models, a large class of version of the menu cost model, and then we leverage that as much as we can, and we get like this nice representation. So something that is kind of interesting is that there is a one-to-one mapping between the curvature of the hazard and different statistics that people have been using before in the data. So for example, the kurtosis of price changes condition on the other moments as a one-to-one mapping into the curvature of the hazard. So the route, and for example, if you do other twists of the model, you add Kimball, you add strategic complementarities, all of that will be embedded into the curvature of the GHF. So the route that we take here is that we estimate that from data. And then you can give me different models that have a rationalization for that curvature.
Okay,
Thank you.
The pointer doesn't work, right?
Yeah. It's going to be the red dot.
It does work. All right. Thanks to the organizers for having me on the program. This is a great privilege to be here. This is joint work with Peter. So it's not Peter presenting, I'm sorry. Peter's sitting over there, but he is ready to take all the difficult questions. And there's also Ernesto for the really difficult ones, and Anton and Gallo who stayed at home. I'm going to talk again about state-dependent pricing, so this fits in nicely. Lots of things I'm going to say are reminiscent of what we just heard. But while the previous paper took a positive and empirical approach to the question, I'm going to take a normative approach to state-dependent pricing, and I'm going to ask what optimal policy should do. And I'm going to conclude that it should strike while the iron is hot, by which we mean that it should lean particularly forceful against inflation when inflation is high. So the motivation is basically the same as the motivation slide in the previous presentation. So I'm not going to click on that link that is there, because you've already seen the time series for inflation and frequency. So in the US, inflation has spiked just below 9% if you take the normal consumer price index. The frequency underlying the consumer price index has gone up from 8.7 to 22 point, I forgot, something, 5. So more than doubled. This is monthly frequency of price changes. So we had this huge spike in inflation and an even larger spike, well, even larger, and then a very significant spike also in the frequency of price changes. Now, when we think about optimal monetary policy and we turn to the textbook, our standard textbook models, they have the concept of a frequency of price changes. That's the Calvo parameter in the standard Calvo model. But it's just a parameter and it's constant. So what we are trying to ask here then is, well, what if it's not constant? What if there's endogenous variation in frequency? In particular, how should optimal policy be conducted if there's endogenous variation in frequency? And in particular, we would expect this to matter the most when we are in a large inflation surge, such as the 2022 episode. All right, that's the question. How can we answer this question? Well, we turn to the state-dependent pricing literature, because the state-dependent pricing literature, provides us with models that can explain the endogenous variation in frequency, as we've just seen. Our state-dependent pricing model is going to be a combination of the standard Golosov and Lucas, which is a fixed menu cost model with idiosyncratic firm-level productivity shocks. A combination of that with strategic complementarities, we've just had them, in our case roundabout production, and fat-tailed productivity shocks. These two additional bells and whistles, they allow the model to match moments of the price change distribution in steady state, while simultaneously matching the strong increase in frequency that we observed in 2022. Once we have calibrated our model to match those targets using the US data, we then determine Ramsey optimal policy, and we're going to proceed in 2 steps. First, we use a simplified version of the model that is highly analytically tractable to gain intuition. And then we proceed to solve the full model in its nonlinear form under perfect foresight with a numerical algorithm. And we're always going to contrast what we find relative to the standard Calvo model as the kind of benchmark comparison to see what do we learn from state-dependent pricing. And this is what we find. For small shocks, well, first of all, what shocks? First, we're going to consider, so for most of the talk, apart from one slide, I'm going to consider cost push shocks. Why cost push shocks? Well, cost push shocks are those where there's a trade-off between inflation and output stabilization in the standard Calvo model, so these are the interesting shocks to begin with. You can also endogenize these cost push shocks, for example, maybe oil shocks with downward wage rigidities, maybe sectoral shocks and sectoral models. There are ways to endogenize cost push shocks. We are not going to endogenize them further, but we're going to focus on those shocks. If the cost push shocks are small, the difference between Calvo and the menu cost model is negligible. So the prescriptions from the Calvo model basically line up with the prescriptions from the menu cost model, which means that you don't need to use this more complicated menu cost model. You can stay with the standard Calvo model. So for the great moderation period, we didn't need menu cost models when it comes to optimal policy. And you guys have already shown us that we also didn't need it for positive purposes. So basically what we're doing here is extending your positive finding to the normative sphere. But things become interesting, and that's where the focus of this paper lies, when the shocks are large, because then what the menu cost model prescribes is that you should act much more hawkish than you would do under the Calvo model, and much more hawkish than what would be a simple linear extrapolation of your optimal response to small shocks. And that's what we call striking while the iron is hot. You should lean particularly forceful against inflation when inflation is high. Why? Well, as inflation goes up, frequency rises endogenously. As frequency rises, the Phillips curve slope goes up. As the Phillips curve slope goes up, the marginal cost of, or the cost of a marginal reduction in inflation, which is the slope of the Phillips curve, goes down. If something is cheaper, you usually want to do more of it, unless you like it less. I'm going to talk about what you like and what you dislike in a second when I get to the meat of the paper. But the most important element of the explanation is that the Phillips curve is upward bending. And we call this striking while the iron is hot because, you know, the iron, that's our price level. If the iron is hot and you hit it with a hammer, it bends. So if the price level is hot by a lot of inflation and you hit it with your policy instrument, you can really push it down easily, as opposed to when it's cold and it's hard to do so. Great. This is our key result, and if you just take this idea home from this talk, I'd be happy. We contrast those findings for the cost per shock with the TFP shock, and there we find the divine coincidence. So you know the divine coincidence holds in Calvo. It continues to hold here. Why? Well, if your Phillips curve goes through the bliss point of zero inflation and zero output gap, then the shape of the Phillips curve is entirely irrelevant, because you just want to go to that bliss point, no matter whether the Phillips curve is wiggly, upward sloping, downward sloping, doesn't matter. Yeah.
So if you took the standard New Keynesian model, but with time varying frequency, kind of exogenous.
That's one slide further. I'm gonna get there. Here, just here. So to motivate what we're doing, and first of all to motivate how we are going to do it, and also to contrast it with what you would have in Calvo, let me remind you of what we know from the Calvo textbook. How do we do optimal policy there? We have the Phillips curve, which is this animal here. Kappa is the slope of the Phillips curve. It depends on the frequency of price changes, which is 1 minus theta, theta being the Calvo parameter, and y being the output gap. Now, if you consider a variation in theta, or in 1 minus theta in the frequency of price changes, then we get a change in Phillips curve. In particular, if the frequency of price changes, if you raise that by exogenously assuming a larger frequency of price changes, well, you get a steeper Phillips curve until in the limit you get a vertical Phillips curve and you have monetary neutrality. Why? Well, because prices get more flexible, right? The second element we need to do optimal policy is a second order approximation to the welfare function. And you know this looks like pi square plus y square with some weight on pi square. And this weight is a function of the Phillips curve slope. It decreases with the Phillips curve slope. That means if the frequency of price changes goes up, the Phillips curve slope goes up, the weight on inflation goes down. So you care less, you dislike inflation less. Why? Because if prices are more flexible, the same amount of inflation introduces less price dispersion. Now if you take together the Phillips curve on the previous slide and the objective function here, and you derive the first order condition, you get this target rule here, which is what optimal policy should be doing. This is all in the textbook. Now notice that there's no kappa and no theta here anymore. Okay, so these two kappas here, the one here and the one on the previous slide, they basically cancel out, and you end up with an expression that is free of any kappa or of any theta. Which means that if you were to just exogenously vary theta in the standard Calvo model, you wouldn't. But you can do it. You would conclude it doesn't matter. Policy is invariant to those movements, and we're going to contrast what we are finding with this benchmark case. Yes.
But like if you kind of have a time variation, because the epsilon over kappa, that's a bunch of tricks. There's a bunch of forward-looking stuff in there, so it's not totally clear.
No, we haven't.
With exogenous time variation,
yes.
in the frequency,
we would be
neutral now.
Yes, you're right. We haven't done this whole exercise with a time variant theta. I think that's a lot of algebra, indeed. I can't say what it would give us. Yeah.
Sorry, I also then, given this intuition, I guess I was wondering, are you also going to have some results that would show us how the weight on inflation, how much it would need to change to kind of undo the positive effects on the slope of the Phillips curve, in the sense that, at least like I personally find like the positive predictions of the New Keynesian model on the inflation side might be somewhat more palatable than this particular, like the particular source in the MK model of why we care about inflation and the costs of inflation, right? That maybe if we don't take that normative side too seriously, just how much the time variation and the weight for kind of as a exogenously fixed central bank mandate would need to be.
Yeah. So we could do that. We haven't done that.
So just be interesting to get a sense of just the magnitudes involved.
We could have done that. All right. Just to recap. So theta doesn't appear in the optimal policy rule, and the way we've set up the problem is that we have an objective function in only 2 variables, a constraint in only 2 variables, and it's really simple then to get to the optimal policy. I'm going to try to deliver something as simple as that. All right, in terms of the literature, the contribution here is mainly normative. There's a lot of positive literature. Nothing much that I say positively is quite new, perhaps the calibration. Let me move on to the model. Okay, we've just been introduced to one way of writing down this state-dependent pricing model. I'm going to introduce my state-dependent pricing model in just one slide, well, perhaps 2. And I'm going to do it in a different way. I'm not going to show you equations. I'm just going to depart from what you already know and do some minor changes to what you already know. And perhaps you already know this anyway because you have seen these kind of state-dependent pricing models many times. But for those of you who haven't, just take your standard textbook model as it is in the Gali textbook, okay, in discrete time with Calvo pricing in nonlinear form. Remove only one assumption and keep everything else the same, which is Calvo pricing, no more Calvo pricing. Replace Calvo pricing by fixed cost of price adjustments. So now you can reprice every period, but if you want to do so, you have to pay a fixed cost eta. This is a fixed cost for us, just a constant, not a random menu cost. This is a fixed menu cost. That's the difference to the previous paper. What else? We add idiosyncratic quality shocks. So shocks to firm level productivity. Quality, that's a computational trick mainly. Let me not get into the details what exactly that is. And they're going to be fat-tailed. We make them fat-tailed as opposed to normal in order to get the more realistic price change distribution. And finally, we're going to add roundabout production, so intermediate goods in the production function, as in paper cited here, Vasu. And this is a strategic complementarity that helps us bring down the slope of the Phillips curve, which is notoriously high in many cost models. So this will kind of fix that. Great. And what we end up with is our state-dependent pricing model, which is a heterogeneous firms New Keynesian DSG model.
So what do you mean by realistic?
Well, realistic in line with empirical estimates that we take from the literature. I'm going to show you those numbers later.
Not the more expensive realistic, that would be
even smaller.
0.9999 strategic complementarity.
Yes.
Like what?
No, we're not going to have 0.999 because we're going to be at the very, very upper end of the ballpark of empirical of what the literature uses. Yeah, so we would need something else to make it even more flat. You can keep on adding bells and whistles. I'm going to show you the number in a second. Well, in a few seconds, minutes. Okay, the different way to give an overview of the model is to describe the different agents. So the household is the standard guy with Dixit-Stiglitz preferences. He eats, he saves, and he works. He has log linear preferences in labor and utility, or she. The firms, they're going to produce differentiated goods using labor and the final good. That's the roundabout part. As inputs, subject to TFP and cost per shocks, which are aggregate, and those quality shocks at the firm level. And then they have market power. They set prices optimally, subject to fixed costs. And the policymaker, what does he do? He maximizes household welfare, and he has commitment. That's important. We're going to focus on the case of policy and the commitment. Now, how does this model work? What's the mechanics of inside this model? The key agent here is, of course, the firm that needs to set prices. There's a continuum of firms indexed by I. Each morning, those firms wake up with a price that they have inherited from the previous period. Then a shock hits them, and they have to decide what to do. Should they update their price or keep the price? And if they update it, what should the new price be? There is going to be some optimality conditions that determine the new price, the reset price, and the inaction region. And if you combine these optimality conditions with the shock process for the idiosyncratic shocks, you get an endogenously determined price gap, price distribution, which is what you see here on the right-hand side. Now, what's exactly on the x-axis? The price gap that was defined in the previous paper, which is the nominal price of firm I divided by the aggregate price and divided by its idiosyncratic productivity, taken logs, and subtract from this the price P star that the firm would like to have. Okay, the exact same thing, I think, as in the previous presentation. This is the steady-state price gap distribution. What happens? At the beginning of period, a shock happens. The beginning of period distribution is kind of fans out. The guys in the tails are in the action region. They jump to the center, to 0, to a price gap of 0, whereas the guys in the center of the distribution, they stay where they are until they hit in the next period, and perhaps then they're being pushed out to update 1 or 2 periods later. So this is what happens in steady state. Every period you jump, you're pushed outside, you jump back to the middle, you drift to some side until you update again. The frequency of price changes is the blue area, the shaded blue area. Now what happens with the big shock? Same as before, just that before we had this U-shaped hazard function. Here we have a, well, what is this? I don't know. It's the step function. It's 1, 0, 1 hazard function. I'm not plotting it. But everyone inside stays, everyone outside updates. What happens after a large shock? Well, there's more people in the updating region, in the action region, and the frequency of price changes endogenously increases. And it's exactly this mechanism that we're going to analyze from a normative point of view. So now we're going to do optimal monetary policy. How am I doing with time? Oh. First, I'm going to do the simplified version of the model, because I want to be as close to the textbook as possible. In fact, I think one can teach this to undergraduate students, this part of the model. So how do we do it in Calvo? In Calvo, I've already shown you how we do optimal policy. We have a planner who selects inflation and output to maximize quadratic welfare subject to a linear Phillips curve. So one objective, one constraint, just 2 variables. That's about the easiest optimization problem that you can think of. Well, I want to do something similar, but how can I do it? If I were to linearize, I would throw the baby out with the bathwater because I want to document those nonlinearities, so I can't linearize. So we thought, what else can we do? And we came up with the idea of making things tractable by, instead of truncating nonlinearities, we are truncating dynamics. Now we're cutting away the dynamics. There are dynamics here because the Phillips curve is forward-looking, and here the Phillips curve, in fact, is a whole block of equations that is also backward-looking because of the price distribution being a state variable. We're going to truncate all of these complications with one simple assumption, which is the day is as I've just described, but then at the end of the day, so you wake up, you set your price, you sell, and then that's the end of the day, and you go to bed. But overnight, the firms are still awake and they can reset their prices for free. Okay, and then the next morning they are hit by a shock again, and the same story repeats. And this means that our model is simplified from a dynamic, complicated model with lots of equations and a distribution and a value function to a set of static equations that we can easily handle. This is what people did before with the New Keynesian model. Exactly. This is. I was going to say that next. You've probably seen that for Calvo, and we're just doing the same thing for the many cost model. The benefit is that the thing becomes static, and we get nice analytical expressions for the Phillips curve and for the welfare function that are only depending on 2 things, inflation and output, just as in the standard textbook analysis. The standard textbook analysis is linear, but it is forward-looking. Our analysis is nonlinear, but it is static. Okay, this is the Phillips curve. This applies to both Calvo and the many cost model. In the Calvo model, the Phillips curve is looking like linear, but we haven't linearized. It is just the linearity that is inherent in the model is very, very small. The many cost model is upward bending, as you know, and as you know, this is because frequency increases in inflation. Notice that this frequency increase is a second order effect or a higher order effect. For a marginal increase in inflation, frequency doesn't change because the masses at the 2 sides of the distribution that are flipping from adjusting to non-adjusting are exactly offsetting each other. But for larger amounts of inflation, the frequency picks up. And it is this picking up of the frequency which explains the steepening of the Phillips curve. As prices get more flexible, you go towards monetary neutrality. by the way, how do we calibrate the simple model? We want that we have 8.7% of frequency in steady state, and we want that it goes up by 14 percentage points as it did for the US when we reach 10% of inflation. How do we calibrate the Calvo model? The same slope at 0, so same as you guys suggested. What does this mean for the policymaker? The Phillips curve for the policymaker is the choice set. It's his constraint. The policymaker sees the Phillips curve and now has to think which point on the Phillips curve do I want to pick. Okay. So the next thing that we need to look at is his choice set. Sorry, is his preferences. But this is just his choice set. And notice the sacrifice ratio is nothing else than the slope of the Phillips curve. If you're up here and you want to bring down inflation by 1 unit, it's a lot cheaper in terms of output gap than if you're down here. Then you have to sacrifice a lot more output gap. Okay. So what about the planner's preferences? So we're not gonna take some exogenous preferences and think about how we modify the weights. We're just gonna take the welfare criterion. And so this is a representative household, right? So we just take utility and consumption and labor. We substitute stuff until we have an expression only in inflation and output gap. And this is this expression here. So we can write welfare in terms of decompose it in 3 underlying distortions, and each of those distortions will either depend on inflation or the output gap. The first element is the aggregate markup, relates to the aggregate markup, relates to aggregate over or under consumption. Because of the markups of the firms, if these markups are positive, the people are going to consume too little, that's bad for welfare. Okay, the second term here is markup dispersion or price dispersion, because there is price dispersion in the price of the different varieties of goods that we have. Perhaps we eat the right amount of fruit, but we eat too many bananas and too little apples, because apples are too expensive and bananas too cheap. That's markup dispersion. These two terms also apply to the standard Calvo model. This gives you y square if you take a quadratic approximation. This gives you pi square in the Calvo model. And finally, we have to take into account the adjustment costs, which are specific to the menu cost model. We can plot these things. We didn't take any approximations, but we can plot them. They look like pretty much like the first term here. The output gap looks pretty much quadratic. Tells you that you get a pretty good approximation if you take a second order approximation to the thing. It's the same for Calvo and for the menu cost model. Price dispersion is very different. In Calvo, it increases in inflation in a square manner, but in the menu cost model, it decreases in inflation. Why? As inflation goes up, more and more people adjust their prices. Everyone who has adjusted their prices has a price gap of 0, so has the same price. So as more and more people accumulate at this point of 0 price gap, price dispersion actually goes down. This effect is not dramatic, it's quite small, but it goes the opposite direction. Does this mean that now inflation is a good thing to have? No, it is of course not, because these adjustments don't come for free. They have to be paid for in terms of adjustment costs, and we also have to take them into account, and the adjustment costs are much larger quantitatively than that effect over here. So if you want to have the total effect of inflation on welfare, in the menu cost model, you have to add up the two blue lines, and you'll still get something that looks approximately quadratic in inflation. What's the parameter? So we calibrated it in order to get a frequency of price changes of 8.7 in steady state and a frequency of price changes at 10% inflation of 8.7 plus 14%, 23.7. I think, so in the simple model, I don't know it for sure, and in the other model, we have the number in the paper, but from the top of my head, I remember that my co-authors thought it was reasonable. You remember it? Less than 1%. For the full model. This is the simple model, which is not meant to be taken serious quantitatively. Yes, I've also, in the simple model, I forgot to say that, it was on the slide, I also cut away those bells and whistles, so there's no roundabout production here, there's no non-normal shock, so we made this as simple as possible, I forgot to say that. And hence the calibration is not the same as that of the full model. Sorry. Okay, now if we take these 3 panels together, we can look at welfare as a function of output gap and inflation. This would be a 3-dimensional picture, which I don't like too much, which is why I'm showing you here the isoquants of the welfare function. Okay. These are basically our indifference curves of the planner. They look like circles in the Calvo model, right? Because x squared plus pi squared gives you some sort of circle shape. Yeah, you get it. And they are still circles, just more elliptical, squeezed circles for the menu cost model. Why? because in the menu cost model we dislike inflation less. Yeah, so or we tolerate inflation more. So the planner under menu cost is more inflation tolerant because of the fact that inflation is less costly, of course. Okay, and now we're gonna do what, that's why I think you can teach this to students, what people do in Micro 101. We take our indifference curves, we combine that with our budget constraint, our Phillips curve, and we derive optimal policy. So this is the Phillips curve for the Calver model. Let's start with Calver with the easier case. The Phillips curve for the Calver model don't no longer go through the origin, because this is the Phillips curve for a very large cost push shock, which displaces the Phillips curve to the left. Next, we take our indifference curves, and we find that indifference curve, which is exactly tangential to the Phillips. Sorry, we take our isoquants. From the welfare function, we take the isoquants. We find the isoquant, which is tangential to the Phillips curve. Okay, so like. This is our indifference curve, this is our budget constraint. We find the optimal point A. Okay, that was easy. Now we found the optimal inflation output configuration for this particular cost push shock. The implementation of this I'm going to get to in a second. Now we can do this for different levels of the cost push shock, which will shift to the left and to the right, the Phillips curve. We always find the relevant isoquant, and we get this target rule. Okay, this target rule is again looking very linear, even though nothing here has been linearized. And this has the same slope as 1 over epsilon as what you would get in the linearized model. At 0 it has the same slope. Great. That was easy. For the menu cost model we have a different Phillips curve. At 0 they coincide, but for more than 0 inflation they differ, and in particular the menu cost model was upward bending, remember. And we also have different isoquants. They are steeper because the central bank is more tolerant to inflation. So these two things go in opposite direction. Which one dominates depends on where exactly you look at. So over here, the steepening of the Phillips curve is more important than the steepening of the isoquants, which is why point B is below point A. So this is a much more hawkish configuration, and more negative output gap and a lower level of inflation. Whereas if we go over here, so shift those two Phillips curves over here, towards the origin, they coincide. There's no more differences in Phillips curve slopes. The only difference that remains is the difference in the objective function. You're still more inflation tolerant, which is why over here you actually behave more dovishly under the menu cost model. This small area here already looks kind of small in the simple model. In the quantitative model, this area will be no longer visible. It will be so tiny that you can't see it anymore, which is why we say for small levels of inflation, there's no difference in the policy prescriptions. So you can go with Calvo. No need to solve this much more complicated. Well, now it's not yet complicated because it's all static, but in a dynamic version it will be complicated. So you can go with Calvo, but for large shocks, you get this strike while the iron is hot feature. You want to lean more aggressively against inflation. What we have done in terms of playing with the objective function is to replace the objective function with the Calvo objective function. So we have the Phillips curve from menu cost, the objective from Calvo. This allows us to isolate the effect of the Phillips curve, and we get an equally concave target rule. It's even steeper because down here they now necessarily tangent. Okay, how do we implement this policy? The policymaker doesn't pick output, he doesn't pick inflation, he picks interest rates, right? So we can take the IS curve and back out the real interest rate that implements this configuration. We can have this target rule in terms of, instead of writing the output gut here, we write the real interest rate here, and then we flip the axis and we get this figure, which tells us for each inflation level what should be the real interest rate under the optimal policy. And we can once again see that for, say, 10% of inflation, you behave much more hawkishly in the menu cost model. Great. This is the simple model. Now I have a slide to summarize what I said. I think I've said most of it, but this was the simple model. I want to stress once again that it's not a trivial result. You could say, oh, of course, the Phillips curve is upward bending, we will get this result. Well, this is only true if nothing happens to the welfare function. But in the Calver model, what would happen, and we could do this exercise here, I don't have it on the slides, but in the Calver model, you change the Calver parameter. Both the slope of the Phillips curve will change, the slope of the indifference curve will change, and you end up with the same red line that you see here. So it's not a trivial result. You need to do the micro foundations at least once, then afterwards you can keep on using your objective function from the Calvo, but you couldn't know this ex ante. All right, now you can still say, okay, but this was your simple model. It was static. You've cut away lots of things. Is this quantitatively relevant? So now we move to to the full model, which we have to solve non-linearly. In terms of calibration, let me just tell you what we target. Here's, by the way, this number. No, there's the kappa on the slide that you were asking for, the adjustment cost, but it's not in terms of, where is it? I don't even find it. Yeah, but it's not in terms of, it's not in terms of output. Yeah, but it's not in terms of anything. You cannot compare it to steady state output, which is what you would need to know. So it must be the number that Peter said. But this is what we target. So we target the frequency of price changes in steady state, meaning in long run average. We target this. It's monthly. Yes, there's a monthly frequency. So that means the price is updated once per year, basically, more or less. This is the average of the 20 years prior to or 10 years prior to the inflation spike. The size of price changes is 8.5%, whatever. The kurtosis is 4. These are the 3 targets that we match. And then we match this 14% increase in the frequency that we observed from before the inflation spike to the peak of the inflation spike, when inflation reached 10% or almost 10%, approximately 10%. What do we get in terms of Phillips curve slope? 0.08. This is the number from Hazel and Corthers, the range of values that Hazel and Corthers report as what the literature has previously found. They are at the bottom of this.
What is your strategic
20, so it's 0.2 of labor and 0.8 of intermediate inputs. So that's within within the range between, I don't know, 15 and 30 what people use, I think. Yeah. So we have 20%. So what is important to get these numbers right? The fat-tailed idiosyncratic shocks are important. And the second thing is that the strategic complementarity. The strategic complementarity makes the Phillips curve much. So the first one is mainly helping us with those moments here. The strategic complementarity, the roundabout production, mainly helps us with the Phillips curve slope, which is actually not a target. But anyway. And it also helps us with the shock size that we need in order to get into the nonlinear region. If we didn't have this flatter Phillips curve, we would need very large shocks to get into the nonlinear region of the model, into the visibly nonlinear region of the model. Great. Now we have some parameter values. Now we need to solve this model under optimal policy. This is the heterogeneous agent model, and on top of it we need to do optimal policy, so this is not straightforward. But we have a new algorithm that can do this, and I think it is generally applicable for SS-band types of models. Let me not talk about methods. We've had a lot of method talks already. Let me talk about the story. Mm-hmm.
You're putting it in diner, so it's kind of like a small state space kind of thing. So how large is this state space?
So the state space is not really relevant since we're in the sequence space. So we're doing perfect Fawcett transitional dynamics. The number of variables is relevant. And the number of variables is something like 150. Because we don't need too many grid points, because we do lots of smart things about interpolation and continuous approximation of stuff. So everything is smooth, like what you said, without even introducing an additional shock. That there we do some things that I'm happy to talk about later if you have questions. But this is very technical and boring. But I think it's exactly what you tell your students, you said. Or at least some of it. Okay, so now before I showed you inflation and output for a given cost per shock, that was just one point in my chart. Now I have to show you, unfortunately, impulse responses. I hate to have to do this. This is more hard to read, but in dynamic models, that's what we have. So these are the impulse responses to a cost per shock in the menu cost in blue. That brings us up to 10% inflation under the optimal policy. And now we compare that to the Calvo model with the same cost per shock. In the Calvo model, for the same cost per shock, you get more inflation and you get less of the output gap, at least throughout the first, 10 months. So the same as in the static model, just now that it holds dynamically, you have less inflation in the menu cost model and more output gap. How do you implement it? Your real interest rate is higher than it would be in the Calvo model. And you can also see the nonlinearity of the model here. So the target rule, remember the target rule was linear in Calvo, but concave in the menu cost model was nonlinear. You can also see that nonlinearity here in the yellow line. The yellow line is a cost per shock which is small, but we've scaled it up such that if the model were linear, they would be on top of each other. Yellow and blue would be on top of each other. They are not on top of each other. The yellow line is above, so you have more inflation and less output gap for small shocks. So you behave more dovishly for small shocks than you do for large shocks. So it's exactly the same thing that what we found for the simple model, just that now it's true dynamically. We can make this figure a little bit simpler by compressing the dynamics into summary statistics. So let's say instead of showing inflation as a path, let's just show impact inflation. If you prefer to accumulate inflation across 2 years, fine, we can do that too. So we just cannot accumulate it across all years because we have price level targeting in the long run. Yeah. But we can accumulate inflation across the first X number of years, and we then accumulate the real interest rate. And this one we can accumulate across all years, or equivalently across 10 years, because after 10 years you're back to steady state. So let's accumulate the real interest rate across 10 years. That gives us the 10-year long-term real interest rate. Why does it make sense to look at the 10-year real interest rate here? This is a model with commitment. So when the planner chooses its policy stance, he doesn't just choose today's interest rate, but he promises a whole path for the future real interest rate, or for the future nominal interest rate, which implies a certain real interest rate. So the policy stance is not the current interest rate that you set, but it's really the whole path of interest rates that you set. And we can summarize this whole path in just one number, which is the long-term real interest rate. This is not a sufficient statistic, but it's a summary statistic that allows us to draw a model, a figure that looks exactly like the one that I've showed you before for the simple model. If inflation goes up in Calvo, you respond proportionally. If inflation goes up in the menu cost model, you respond over proportionally. For small shocks, it's the same. For low levels of inflation, this is where I said you can no longer see that you're more dovish. For small shocks, it's basically the same. But for large shocks, you are almost four times more hawkish at 10%. See, we can isolate it. Oh, sorry, there's a question.
Yeah,
sorry.
so if I compare this with the short run rear rate impulse response from before, like that one seemed to be pretty much uniformly negative over the range you were showing. So, like rear rate cut, I think, on the unless I misinterpreted the figure. So is it that like the rear rate increases?
No.
Oh yeah. So okay. So it increases by like a small amount, very persistent
Yeah.
afterwards.
This is a feature of the Calvo model already. Policymakers hate this. You have to respond with an initial easing and promise future contraction. This is a feature of the Calvo model. If you linearize it or if you don't linearize it, this is still there. So yes, but this is in sum. If you sum it up, it's still a contractionary policy. And this is also a reason to take that sum, because policymakers do not like the previous figure. But I have to dumb it down even more for policymakers. I'm going to do that in a second. We are kind of working for policymakers.
That's actually what they did.
Hmm?
That's what they did. They didn't move nominal rate, except the inflation went up, so they had negative real rates. And then,
Perhaps. So I will not say if they did the right thing or the wrong thing, but perhaps that's what they did. In the full model, we don't have no longer a Phillips curve and just two variables. It now is state dependent, and it's also forward looking. So it's a more complicated object. We can still plot something that we call the Phillips relationship, the relationship between inflation and output gap, and it looks the same basically as in the simple model qualitatively. And again, the frequency response also looks the same as in the simple model. So the mechanics that are underlying this is basically the same as in the simple model. Now, perhaps you say, look, you took fixed menu costs. This is very simple and very nice, but I think you should have used Calvo Plus, like many presentations in this workshop, one presentation in this workshop and many other presentations in other workshops have been doing. Many people like the Calvo Plus model, or perhaps you like, no, actually this one was random menu cost, sorry, I'm getting confused. Some people do random menu cost, some people do Calvo Plus. So is what we're doing robust to those also very popular, or perhaps even more popular, slightly more involved models of state-dependent pricing? The answer is yes, qualitatively. Quantitatively, of course, things change. The flatter the hazard gets, the more linear the model gets, and also the more linear the optimal policy gets. But if those models are so linear, they can no longer explain the high elasticity of frequency to inflation that we've seen in the data. If we force those models, however, by sacrificing steady state moments that we would otherwise target, if we force those moments to have a realistically strong transmission from inflation to frequency, then they will also become much more nonlinear, and they will also predict a similarly nonlinear optimal policy. And these are more involved models. The same is true also with more simple models. So go back to the standard Golosov and Lucas. The same point holds there too. Great. Now, two more things and I'm done. What I promised you in the beginning is the divine coincidence. This is really, I'm going to be more than done in 10 minutes, so any question is welcome. The divine coincidence is really simple. There's not much to say. This is an analytical statement that we have. You don't need to approximate the model in any way. So both for Calvo and for the menu cost model, you can show very straightforward, in a very straightforward way, that the divine coincidence holds exactly. Well, if you have sticky wages, we already know from Calvo that it doesn't hold anymore. You still have to? That we should strike while airing salt. We haven't checked that, but we are working on it in a follow-up paper. So we're working in a multi-sector version of this. Then we can have a labor sector, or a union sector. So we don't. I cannot give you the answer yet, but this is exactly what we're doing right now. Okay, so the divine coincidence holds, and it's an analytical result, and the intuition is what I told you before. You don't care about the shape of the Phillips curve if the Phillips curve goes through 0, 0, which is your bliss point. So that's easy. But for policymakers, everything that I've told you would still have been a little bit too complicated, because they say, look, Ramsey optimal policy, how are we supposed to do Ramsey optimal policy? This is impossible to do in our daily decision making. Give me something easier. So what's easy? A Taylor rule, no? People like Taylor rules. This is the relationship between inflation and the policy stance, the 10-year real interest rate, that our model predicts under Ramsey policy. The thing looks like something that you could approximate with a cubic function. So let's take the Taylor rule, the standard Taylor rule, some coefficient on the past nominal interest rate, on the output gap, and on inflation. And the only change that we're going to do, because more they will not digest, is that we're going to add here an additional component phi square, phi f pi square. So phi pi is the normal response coefficient to inflation. To this we add a term that is square in inflation. And this means that if inflation deviates from the target, you will respond more strongly to those inflation deviations. Okay? So this is a very practical implementation of striking when the iron is hot. When inflation is high, you strike stronger. So let's consider such a deviation of the Taylor rule. And let's calibrate the Taylor rule to match this figure up here. So first, the linear coefficient. We pick the linear coefficient so that we match this figure at 0. That is for small shock. So we want to get as close as possible in terms of this, which is not a sufficient statistic, but in terms of this summary statistic, we want to get as close as possible to the Ramsey policy. We get a coefficient of 2.2. The other coefficients, we just keep them fixed at empirical values. We get a coefficient of 2.2, which is actually not too far away from estimates. So perhaps our policies are not so far away when it comes to small shocks. They're pretty good. And the second coefficient, the nonlinear coefficient, we pick it such that we match at 10% this figure. And it so happens that we almost match it everywhere perfectly. When we continue that line, we stop matching it perfectly, but between 10 and 0, we almost match it perfectly. The number 135,000, 2.2 I think you can interpret, no? That's clear. That's relative to our standard 1.5, that's clear. 135,000, what does this mean? It means that if we had 10% inflation, we respond 6 to 7 times more strongly than we would have responded if we would have just used the standard linear rule. Yes, then that number becomes, yes, yes. Yeah. But I think even better than to just look at the rule is like, okay, what do outcomes look like under this rule? Because of course you never actually go to 10% inflation once you adopt this rule. So we do the following thought experiment. And this is a thought experiment. It's not a description of what happened in 2022. It's just motivated by what happened in 2022. So let's say the policymaker was pretty smart. In 40 years of great moderation, he learned the optimal policy rule. And he uses the optimal policy rule. It's just that he never saw large inflation, so he has forgot about the nonlinear coefficient. So he has phi f0. And then a shock happens when that brings inflation to 10%, a cost push shock. How would the economy behave in that case? Well, that's a blue line. Okay, 10% inflation, 2-3% of output gap. Now, what about if the policymaker would have done the optimal policy? That would be the red line. The optimal. It's not the optimal policy. It's not Ramsey policy. It's the approximation of Ramsey policy with that very simple tweak to our otherwise very realistic Taylor rule. Well, then we would get the red line, about half as much inflation at the peak, I don't know, 50 basis points more in terms of output gap, 25 basis points more in terms of the nominal rate. You don't have to sacrifice much output gap to get this large reduction in inflation because the sacrifice ratio is currently low. Existence? I mean, existence. So locally, we can do this locally, and locally everything is fine. I mean, 2.2 is, satisfies the Taylor criterion, so no problem. I'm not aware of what would be the nonlinear counterpart to the linear condition that you're referring to, so we didn't check it. For sure, if you make the shock sufficiently large, well, I'm not sure, but I would be pretty sure that at some point you no longer have an equilibrium. But 10% of inflation is not yet a very large shock in that sense. So linearly, it's fine. All the conditions are met. Globally, I can't tell you. I can just tell you that we find an equilibrium.
Similar question, because we know literature is Markov's legislative model with indicator flavor. They are very hard time to guarantee the uniqueness of the equilibrium. That's even exogenous switching. In your case, it's endogenous, right? Inflation level goes up then.
Well, it's not switching. It's a gradual, smooth transition, really. So there's no two regimes. But yes, I mean, I can't tell you much more on this, but we didn't have ever problems with finding an equilibrium. Is it unique? We have never found a second equilibrium. But globally, these kind of conditions are hard to verify. No? All right. In terms of welfare, how much better is it to follow that nonlinear rule? Well, it gets you 50% closer. So the welfare distance between the linear rule and the Ramsey rule, you can close 50% of that welfare distance by just that one single tweak. Okay? So you're not doing the same as well as Ramsey, but you're doing 50% better than what you would be doing in case of in terms of the linear rule. And notice that there's no trade-off here. This rule prescribes the optimal policy for small shocks. This nonlinear coefficient only kicks in for large shocks. So you don't have to do always more hawkish because in bad times you want to be more hawkish. No, you will only be more hawkish in those very specific circumstances. So there's no trade-off between doing it right in normal times and doing it right in bad times. There's a question.
So one question, the difference between the nominal interest rate trajectory is 25 basis points, but in terms of real interest rate must be quite significant, no?
Yes, because inflation is much different. Yeah. I guess. Yeah. Okay, I think this is it. Am I on time? Yes. So I think if there are any more questions, I would conclude. We study optimal policy in a menu cost model, in really a simple menu cost model, I would say. The divine coincidence holds for TFP shocks, everything as in Calvo. If you thought that, like we had previously an estimation, decomposing the different shock sources. I mean, if these are monetary policy shocks, of course, they don't exist under optimal policy. If these were TFP type of shocks or preference shocks, you would have the divine coincidence. But if they are cost push shocks, well, for small shocks, same as in Calvo, you lean against the wind. For large shocks, you strike while the iron is hot. So you lean particularly strongly against the wind because you want to exploit the temporarily low sacrifice ratio. And the Taylor rule that responds more aggressively to inflation when inflation is high doesn't perfectly approximate this, but at least gets us a step closer. And that's it. Thank you.
Thank you. Time for one question? Anything?
Can I just, yeah. Suppose you have a nonlinearity in aggregate demand. How would your result be robust? Because it's not in the model.
And nonlinearity in aggregate demand.
Yeah. So you have a credit constraint that becomes underdefined because you rise the default state. So
so much that some firms cannot rise their price as much as firms subject to monopolistic competition. They have this financial situation that becomes fine.
I would say the answer would be the exact same as that what you would get under Calvo, just that you would hit this constraint earlier. So yeah, we haven't done any such thing, but this is not specific to this. So the answer to your question is not specific to this setup.
No, that's my premise. If you add that on top of the feature you have.
Well, I guess you can add some certain nonlinearities that would tell you that you shouldn't strike as hard. But also in Calvo, they would tell you not to strike as hard. So the Calvo optimal policy rule would probably also become more dovish, so become more steep, and the steepening of our target rule would then probably be partially reversed. But I would expect to see a similar qualitative difference between Calvo and the menu cost model as what we.
It's out of the box.
Thank you very much.